Hello and welcome to Sleep Science Space, a place where curiosity slows its pace and science unfolds gently, giving your thoughts room to soften and drift. Tonight, I'd like to guide you toward a destination few humans have ever reached in person, even though its name echoes through our imaginations. It exists here on Earth, yet it feels farther away than the moon or Mars. A realm so deep, so dark, and so unfamiliar that for most of human history it lived only in stories and speculation. We're traveling to the deepest known place on our planet, the Mariana Trench. Before we begin that slow descent, take a moment to notice where you are right now. Are you listening from somewhere near the ocean, where the rhythm of waves is part of everyday life? Or are you far inland, where the sea feels abstract, something known mostly through images, maps, or memory? Perhaps you've stood at the shore before watching water stretch endlessly toward the horizon and wondered what lies beneath that moving surface. Or maybe the ocean has always felt distant to you, a vast mystery seen only on screens. Wherever you are for the next little while, we'll drift together into a part of the ocean almost no one will ever witness firsthand. It's a curious thought, isn't it, that more than 70% of Earth is covered by water, yet the world beneath the waves remains less familiar than distant planets. If you enjoy these unhurried journeys, explorations that invite learning, reflection, and maybe even sleep, I'm grateful you're here. Simply being present with your curiosity is enough. Now let's begin to loosen our connection to the surface. Imagine yourself downing by the edge of the sea. The water looks calm, maybe dotted with seabirds or distant ships. It feels familiar and peaceful, but beneath those gentle waves is an entirely different world, layered downward in ways that are hard to picture. Imagine slipping below the surface, moving past the sunlit waters where fish flash by and reefs glow with color. As you descend, the light slowly weakens. Colors fade. Reds disappear first, then yellows, until everything takes on shades of blue and gray. Keep drifting downward, and you pass into twilight, a dim zone where sunlight is only a memory. Shapes grow softer, movement slows, then even that faint glow vanishes completely. You enter a region of permanent night where darkness is total and unbroken. This is the true deep ocean, a place untouched by day or season. If you continued even farther, far beyond where most life seems possible, you would eventually reach a vast lie in the ocean floor itself, a long, narrow valley carved into Earth's crust deeper than the tallest mountains are high. This is the Mariana Trench. It lies quietly in the western Pacific Ocean, east of the Philippines and south of Japan, curving across the seabed like an ancient scar. From end to end, it stretches for more than 1,500 miles, roughly the distance between Los Angeles and Kansas City. Yet its length is not what makes it extraordinary. It is the depth that captures the imagination. At its lowest point, known as Challenger Deep, the trench descends nearly 11 kilometers below sea level. That's about 36,000 feet. If Mount Everest were placed inside it, the mountain's peak would still sit more than a mile beneath the ocean's surface. Just pausing on that idea can feel dizzying. All that water pressing down from above. Down there, The pressure is more than 1,000 times greater than what we experience at the surface. It's a force so immense that it would instantly crush an unprotected human body, warp metal, and collapse the structures built for ordinary conditions. And yet, despite this overwhelming weight, the trench is not empty. It exists in quiet darkness, holding secrets shaped by pressure time and the slow movements of our planet. For now, you don't need to picture anything more than that gentle descent. Let the numbers fade into feeling, a sense of depth, stillness, darkness that isn't frightening, just vast and calm. As we move deeper in this journey, there will be more to discover. But for this moment, simply rest here, suspended between the surface you know and the hidden world far below, letting your breath slow as the ocean around you grows quiet and deep. For early civilizations, the ocean marked a boundary between the known and the unknown. Maps faded into blank space long before anyone imagined what the seafloor looked like. Beyond the familiar coastlines, there were only guesses and fears. Sailors navigated by stars and instinct, not knowing how deep the water beneath their hulls truly was. The idea that the ocean floor could drop away into immense chasms simply wasn't part of their understanding of the world. It wasn't until the 19th century that humans began to seriously question just how deep the ocean might be. Early attempts to measure depth were simple and slow. Weighted ropes were lowered over the side of ships, sometimes taking hours to reach the bottom if they reached it at all. Often the rope would drift, snap, or come back without touching anything solid. These failures hinted that the ocean was far deeper than anyone had assumed. Still, the Mariana Trench itself remained hidden far beyond the reach of such crude methods. The first real clues came with the development of sonar in the early 20th century. Instead of relying on ropes, scientists sent sound waves downward and listened for their echoes returning from the sea floor. Suddenly, the invisible world below began to take shape. Charts revealed vast plains towering underwater mountains and deep valleys carved into the crust of the planet. Among these features was a region in the western Pacific where the echoes took much longer to return. This was the first scientific hint of the Mariana Trench. As sonar mapping improved, the picture became clearer. The trench was not a simple hole, but a long, narrow scar created where one tectonic plate slowly slides beneath another. This process, called subduction, has been shaping the trench for millions of years. Inch by inch, the Pacific plate is being pulled downward beneath the Philippine Sea plate, folding the Earth's surface into a deep arc. The Mariana Trench is not dramatic in the way a cliff is dramatic. It forms slowly, silently, driven by forces far beyond human timescales. Even with sonar data, actually visiting the trench was another matter entirely. The pressures were extreme, the darkness absolute, and the distances immense. For decades, the deepest parts of the ocean were explored only indirectly through instruments lowered from ships or cameras sent down on long cables. These glimpses were brief and grainy, like peeking through a keyhole into another world. Then, in 1960, two humans finally made the journey. Jacques Piccard and Don Walsh descended into Challenger Deep aboard a small submersible called Trieste. As they sank deeper, the pressure outside grew immense, the hull creaking and groaning under the strain. At one point, a window cracked, sending a shock through the vessel. Yet they continued drifting downward for nearly 5 hours until they reached the bottom. What they found was not the barren wasteland many expected. The seafloor was quiet flat and covered in fine sediment like pale dust settled after a storm. They even reported seeing life, a flatfish, moving slowly across the bottom, though this observation is still debated. Regardless, their journey proved something extraordinary. Humans could reach the deepest place on Earth and return. Since then, only a handful of crewed missions have followed. Most exploration is now done by robotic vehicles patiently descending into the darkness, sending back images and data. These machines have revealed strange, delicate creatures adapted to crushing pressure, translucent animals with soft bodies, snailfish that thrive where nothing else seems able to, tiny organisms feeding on chemical energy rather than sunlight. Life, it turns out, does not give up easily, and still much of the trench remains unexplored. Each mission uncovers new questions. How do these organisms survive such pressure? What do their biochemistries tell us about the limits of life? Could similar forms exist beneath the icy oceans of distant moons, like Europa or Enceladus? In this way, the Mariana Trench connects the depths of our own planet to the search for life beyond it. There is also a quieter, more unsettling discovery. Even here, at the deepest point on Earth, signs of human presence have been found. Plastic fibers, chemical pollutants, traces of our activity carried by currents all the way down. It's a reminder that no place on this planet is truly isolated anymore. The trench may feel remote and timeless, but it is still part of the same interconnected world. As we continue to drift downward in thought, there's no need to hold on to every detail. Let the facts settle like sediment. The trench is deep, ancient, largely unseen, a place shaped by immense pressure and slow geological time. It reminds us that Earth still holds frontiers not above us in the stars, but beneath our feet, hidden under miles of water. For now, imagine the surface far above waves, moving gently, unaware of the silent world below. Imagine the darkness growing thicker, calmer, quieter. There is no rush here. The Mariana Trench has waited millions of years. It will wait a little longer as we continue this slow descent, letting curiosity soften into calm and thought gradually give way to rest. The shoreline has always been a comfortable edge. When you stand on solid ground, you can watch the waves arrive and retreat, hear their rhythm, and feel their steady pull. Everything feels understandable there. But once a vessel traveled far enough that land slipped out of sight, something shifted. Familiar reference points vanished. No trees, no mountains, no roads. Only water in every direction, moving and breathing in ways no one could predict. For early sailors, that vast openness was unsettling. The ocean did not offer signs or boundaries. It seemed infinite. So when maps ended and knowledge failed, imagination stepped in. Empty spaces were filled with drawings of serpents, enormous fish, and unknown beings. These were not careless decorations. They were expressions of uncertainty. When people did not know what existed beyond the horizon, they assumed something powerful lived there. Across cultures, the sea was more than water. It was a force with personality. Polynesian navigators learned to read its swells and stars, turning it into a living map that carried them across enormous distances. In northern traditions, the ocean was colder and harsher, a domain of giants and spirits. In ancient Greece, it belonged to Poseidon, unpredictable and easily angered. Around the world, similar stories emerged. Leviathans, krakens, creatures that pulled ships into darkness below. These myths were not created for entertainment alone. They were tools for understanding fear. When something cannot be measured, named, or controlled, the mind gives it form. And for most of human history, the depths of the ocean could not be measured at all. Even relatively shallow waters were beyond reach. Sailors lowered weighted ropes, hoping to feel the seabed. Near the coast, this sometimes worked, but farther out, currents twisted the line, weights drifted, and the rope vanished into the water without ever finding bottom. Picture standing on the deck of a wooden ship, hands burning as rope slides through your palms for hours. You don't know how far down it goes. You don't know if it will ever stop. Eventually, you are forced to accept that the bottom may as well not exist. For centuries, this was the limit of human reach. Everything below was guesswork. The seafloor might as well have belonged to another world. And yet, curiosity never disappeared. As humans began mapping continents more precisely in the 16th and 17th centuries, questions turned downward. If the land could be charted, why not the ocean? But while coastlines filled in with detail, the seas remained blank. One famous phrase captured this uncertainty perfectly: "Here be dragons." Whether anyone truly believed in dragons mattered less than the meaning behind it. Past this point, knowledge ends. For those who lived by the sea, this uncertainty was personal. Fishermen felt invisible forces moving beneath their boats. Traders watched storms rise without warning. Sailors learned that the ocean had moods calm one moment and violent the next. The surface gave hints, ripples, swells, shifting colors, but never explanations. Beneath it all, something vast remained hidden. People learned to navigate across the water, but rarely thought of what lay below. The ocean became a ceiling rather than a floor. Eyes stayed fixed on the horizon, not on the depths beneath the hull. And through all of this unknown and untouched, the Mariana Trench waited. It lay far from ancient trade routes, distant from the coastlines where civilizations gathered. In a quiet stretch of the Pacific, it sank deeper than anyone could imagine. While stories filled the waves above and ships crossed unknowingly overhead, the trench remained invisible, not feared, not named, not measured, simply there, as in silence long before anyone was ready to look down and ask how far the world truly falls. For countless generations, it existed only as absence. The deepest place in the ocean lay unseen, unheard, untouched, resting in darkness, while human history unfolded far above it. Empires rose and faded, languages formed and disappeared, yet this vast feature of the planet remained completely unknown. That such an enormous part of Earth could stay hidden for so long tells us how distant and unreachable the deep sea truly was. Early efforts to understand the ocean now feel almost gentle in their simplicity. Sailors lowered heavy objects tied to long ropes, watching them slip silently into the water. The line would unwind and unwind, disappearing into blue depths until eventually there was no more rope left. Still no bottom. Sometimes the rope snapped under its own weight. Other times it went slack, suggesting contact, though no one could be certain whether it had reached the seafloor or merely caught on something unseen below. Each attempt brought a mix of frustration and quiet awe. To stand on a wooden deck and realize there might be miles of water beneath your feet and land beneath that which no human hand could ever touch stirred something deep in the imagination. Slowly, these measurements and added fragments to human knowledge. But most of the ocean floor remained a mystery, uncharted and unreachable. To people of those eras, the deep sea felt almost unreal. It became a place of speculation rather than observation. Some imagined strange creatures living far below others, believed the depths held secrets about the very structure of the earth. The idea that the ocean could plunge deeper than the tallest mountains rose was beyond comprehension. And so the sea remained both a boundary and a symbol, the physical edge of exploration and the mental edge of understanding. When knowledge is missing, the human mind fills the space. Without evidence, explanations took the form of stories. Some believed the ocean had no bottom at all, that it fell endlessly into nothingness. Others assumed it must be shallow everywhere, that land could not be far below the surface. Over time, guesses hardened into beliefs. Beliefs shaped worldviews. The ocean became something to fear, something to respect, something powerful, precisely because it could not be known. Even as the 19th century brought faster ships and expanding trade, the deep sea continued to resist discovery. Humanity learned to cross the oceans with confidence, yet still had no way to truly look beneath them. It wasn't until new tools appeared that this barrier began to weaken. Stronger materials, better instruments, and eventually a revolutionary idea using sound instead of touch. With the arrival of sonar in the 20th century, the silence below was finally answered. Sound waves traveled downward and returned, revealing a seafloor far deeper than anyone had expected. Bit by bit, the blank spaces on the map began to fill in, and among those discoveries was the Mariana Trench emerging not suddenly, but slowly as data accumulated and understanding deepened. Before that moment, however, the trench existed only as empty space on a chart, and empty spaces have their own gravity. They draw imagination, fear, and wonder. The edge of the map has never been just a line on paper. It is a boundary of thought, a place where certainty ends and curiosity begins. For centuries, the ocean itself was that question mark, and hidden within it, the Mariana Trench remained its most guarded secret, waiting quietly far below the reach of rope light or sound. Only recently did it pass from legend into knowledge. What we now treat as a statistic, a depth measured in numbers, was once nothing more than an untold story. And it is worth remembering how new that knowledge truly is. For most of human existence, the abyss beneath the Pacific was not something we understood, it was something we imagined. A silence beneath the waves, patient and unmoving, waiting for the moment when curiosity would finally learn how to listen. When humanity first began to measure the ocean with greater intent, curiosity was only part of the story. The motivation was practical, even urgent. Sailors needed to know how deep the water was near shorelines to keep ships from running aground. Naval planners wanted reliable information for anchoring fleets and charting safe routes. Fishermen sought clues about where life gathered beneath the waves. Depth, it turned out, mattered. At first, these needs were answered with the same simple technique used for centuries. A heavy weight, often made of lead, was tied to a long rope and lowered into the water. This method, known as sounding, was straightforward and dependable in shallow coastal areas. But once ships ventured into the open ocean, it quickly revealed its limits. Using rope to measure the deep sea was like trying to measure the height of the clouds with a pole. The deeper the water, the more impractical the method became. Ropes grew heavy under their own weight. Currents pulled them sideways instead of straight down. The ship itself pitched and rolled, making precision impossible. Imagine standing on the deck of a wooden vessel, waves rocking beneath your feet, wind pressing against the sails. Coil after coil of rope slides through your hands and disappears into the dark water below. Minutes pass, then more. No one knows if the weight has reached the bottom or is still drifting somewhere in the vastness beneath the ship. Even when the rope finally seems to stop, uncertainty remains. Did it truly touch the seafloor? Or did it catch on an underwater slope, a ridge, or a floating current? Despite these challenges, people continued to try. In the late 18th and early 19th centuries, expeditions grew more deliberate. Nations with growing naval ambitions, especially Britain, began to see value in understanding the depths as part of their expanding influence at sea. This slow shift towards systematic exploration would eventually give birth to an entirely new field of science. Long before modern instruments existed, naval vessels carried enormous spools of hemp rope, sometimes thousands of meters long, along with heavy iron weights. The rope was marked at regular intervals using knots, cloth strips, or paint so sailors could estimate depth as it was lowered. Foot by foot, the line descended into the ocean, but hemp rope came with serious flaws. It absorbed water and became heavier as it sank. It stretched under strain, sometimes lengthening so much that any measurement it provided became unreliable. In deeper waters, the rope might break entirely, and when it was hauled back up after hours of labor, it often brought back nothing more than a faint smear of mud or sand. The work was slow, physically demanding, and filled with doubt. Yet it represented humanity's first sustained attempt to touch the unseen floor of the world. By the mid-19th century, interest in the deep ocean intensified for a new reason: communication. The invention of the telegraph sparked an ambitious idea: laying cables across the ocean floor to connect continents. Suddenly, the depths were no longer abstract. Engineers needed to know exactly how deep the seafloor was, how steep it sloped, and what kind of surface the cables would rest upon. A single miscalculation could doom an entire project. Cables snapped under pressure, routes failed, messages went silent. Accurate knowledge of the seabed became essential not just for science but for the global exchange of information. As a result, governments invested more seriously in ocean exploration. Naval organizations in Britain and the United States began launching surveys designed specifically to study the ocean floor. These efforts laid the groundwork for future breakthroughs. They marked the moment when the deep sea shifted from legend toward measurement, from imagination toward evidence. Still, even with all this effort, the deepest places on Earth remained beyond reach. The ropes could only go so far. The uncertainty lingered. The Mariana Trench, far out in the Pacific, remained hidden in darkness, untouched by weight or line. But change was coming. A new way of listening to the ocean was about to replace the need to touch it at all. By the middle of the 19th century, the numbers humans were recording from the ocean had begun to stretch belief. In 1852, the American vessel Dolphin reported a sounding of more than 3,000 fathoms, over 5,000 meters deep. Not long after, the British ship Cyclops logged depths even greater. With each new attempt, sailors realized the sea was far deeper than anyone had once imagined. This was no shallow basin beneath the waves, but a vast vertical world plunging downward far beyond sight or reach. Logbooks began to fill with figures that would have seemed impossible just a generation earlier. Thousands of meters, miles of rope, hours spent lowering weights into darkness. And yet even these impressive measurements barely brushed the upper layers of the true abyss, a depth so extreme that no one yet understood its full scale. A turning point came in the 1870s with the voyage of HMS Challenger. This was not simply a naval journey, but the first global scientific expedition devoted entirely to studying the deep ocean. Between 1872 and 1876, the ship circled the planet, covering nearly 70,000 nautical miles. On board were scientists, engineers, and an extraordinary collection of instruments. Hundreds of kilometers of rope dredging equipment, thermometers, and sampling devices filled the ship's holds. At each stop, soundings were taken. Nets were lowered, mud was hauled up from places no human had ever touched before. Slowly, a new picture of the ocean floor began to take shape. It was no longer imagined as a flat, lifeless plain, but as a complex landscape with mountains, ridges, broad plains, and deep, narrow trenches. In 1875, while surveying the western Pacific, the Challenger crew lowered their line farther than ever before. More than 8,000 meters of rope slipped into the water before the weight finally struck bottom. The depth was staggering. The site was later named Challenger Deep, though at the time no one realized they had reached the deepest known point in Earth's oceans. For those aboard the ship, it was simply another astonishing discovery in a voyage full of them. They measured near freezing temperatures, collected fine sediment, and found evidence that life existed even under crushing pressure. These findings challenged the long-held belief that the deep sea was barren and dead. When the expedition returned, it brought with it years' worth of data, thousands of samples, detailed notes, observations that would fill dozens of volumes. Modern oceanography was born from this effort, grounded not in myth, but in measurement. Yet even this monumental work had its limits. Rope based soundings were still vulnerable to error. Currents could pull the line into a curve. Weights sometimes broke free. Measurements varied depending on conditions. A depth recorded as 8,000 meters one day might appear hundreds of meters shallower or deeper the next. Precision, especially in the deepest waters, remained elusive. The abyss was no longer imaginary, but it was still blurred at the edges, imperfectly known. True clarity would have to wait until the 20th century when a new method replaced rope entirely. Instead of touching the seafloor, scientists began listening to it. Sonar transformed ocean exploration by sending pulses of sound downward and measuring how long they took to return. Because the speed of sound in water is predictable distance, could be calculated with remarkable accuracy. For the first time, the ocean floor could be mapped, not point by point, but continuously. Vast areas could be surveyed quickly and reliably. Trenches, ridges, and plains emerged with a precision never before possible. The deep ocean, long hidden beneath imagination and uncertainty, finally began to reveal its true shape. And with that new clarity, the Mariana Trench would soon be recognized not just as deep, but as the deepest place of all. For the first time in human history, the ocean floor was no longer an idea. It became a shape. Sonar surveys began to reveal what ropes and weights never could. Beneath the waves lay mountains, taller than skyscrapers, canyons, deeper than any valley on land, long ridges stretching for thousands of kilometers, and plunging trenches that seemed to tear the planet open. Among all of these newly revealed features, one stood apart. The Mariana Trench emerged from the data as the deepest place ever recorded. Its contours were traced again and again, each pass confirming the same astonishing truth. More than 11 kilometers below the surface, the seafloor dropped into a narrow, shadowed abyss. What sailors had once guessed at sonar now showed with clarity. The edge of the map had moved, and beyond it was no longer myth, but measurement. Still, it's worth lingering for a moment with those earlier centuries before sound waves and screens, when understanding came only through patience and uncertainty. Imagine those sailors standing on wooden decks, hands raw from rope, watching coils disappear into dark water. They had no guarantee the one would ever reach bottom. No certainty the numbers they recorded were correct. Yet they kept lowering the weights, marking the rope, writing down the depths. Each sounding, whether accurate or flawed, carried the same quiet message. The ocean was far deeper than anyone had believed. To stand there, letting ropes slide endlessly into the sea, was to feel a kind of smallness no mountain could inspire. The ocean was not only vast across its surface, it was immense in its vertical reach, a reminder that our planet holds dimensions we rarely confront. As techniques improved and expeditions multiplied, the ocean floor slowly took shape on maps. It was no longer imagined as a flat, lifeless plain. Instead, it resembled the land above, full of variation and drama. Peaks rose, basins sank, and in one remote region of the western Pacific, the numbers kept returning higher, deeper, more extreme than anywhere else. Ships passing near the Philippines, Guam, and the Mariana Islands began reporting soundings that defied expectations. Lines lowered there seemed to vanish farther than anywhere before. At first, many scientists doubted the results. Ropes could drift, weights could break loose, errors were common. Depths that extreme seemed almost impossible, but the pattern would not go away. Measurement after measurement pointed to the same conclusion. By the early 20th century, it was clear that a vast trench cut through the Pacific seafloor, a feature unlike any other. A scar formed by the slow collision of tectonic plates, where one slab of Earth's crust slid beneath another and disappeared into the mantle. The trench stretched for more than 1,500 miles, curving like a crescent alongside a chain of volcanic islands. These islands already bore the name Mariana, honoring Queen Mariana of Austria. The trench inherited the name, later its identity gradually solidifying as its depth became undeniable. The final confirmation came not from rope, but from sound. During the First World War, the urgency of detecting submarines pushed acoustic technology forward at unprecedented speed. Navies learned to send sound pulses through water and listen for the echoes. What returned carried information: distance, shape, depth. After the war, this technology was turned downward toward the seafloor itself. With sonar, scientists could measure depth with precision free from the sagging curves and stretching fibers of rope. The abyss responded with echoes, and those echoes told a consistent story. The Mariana Trench was real. Its depth was extreme, and at its heart lay a place deeper than any other on Earth. What had once been a blank space filled with dragons and imagination was now a measured frontier, still remote, still dark, but no longer unknowable. And yet, even with sonar tracing its outline, the trench remained untouched, mapped but not visited, known in numbers but not in experience. The deepest place on the planet had finally been found. The next question was inevitable. Could anything or anyone ever go there? With the rise of echo sounding, scientists suddenly gained a tool that felt almost magical. Instead of waiting hours for rope to disappear into the sea, they could now send a brief pulse of sound downward and listen for its return. In mere seconds, the ocean answered back. Throughout the 1920s and 1930s, survey ships crisscrossed the Pacific, their echo sounders quietly tapping into the darkness below. Each returning signal revealed another fragment of a hidden world. When these measurements were pieced together, the illusion of a flat ocean floor dissolved completely. The seabed rose and fell like a submerged continent. Vast mountain chains, later called mid-ocean ridges, stretched across entire basins. Immense plains lay buried beneath miles of water, and in one region of the western Pacific, the floor dropped away so sharply that it seemed to fall out of the earth itself. Here, the Mariana Trench took shape, not as legend, but as fact. No longer dismissed as error or exaggeration, it emerged clearly in the data. Survey after survey confirmed the same pattern: a narrow curving depression plunging deeper than any other place on the planet. Its deepest section, later known as Challenger Deep, would take decades to measure with full precision. But by the mid-20th century, there was no doubt. This was the deepest natural point on Earth. For geologists, the trench was a revelation. It offered visible proof of immense tectonic forces at work where one slab of Earth's crust slowly slid beneath another and vanished into the mantle, a process now called subduction. The planet was not static or finished. It was restless, recycling itself over unimaginable spans of time. For biologists, the trench represented something even more startling, a potential habitat where life endured under pressures strong enough to crush steel in temperatures near freezing and in darkness without end. Conditions once assumed to be incompatible with life were suddenly open questions. And for everyone else, the trench became something harder to define, a symbol of mystery, a place so remote and extreme that it felt closer to science fiction than geography, a reminder that even on our own planet, there were realms as alien as the surface of Mars. To understand why this discovery felt so profound, it helps to remember what else was changing at the same time. In the early 20th century, scientists were only beginning to accept the idea that continents moved. The theory of continental drift was controversial, even ridiculed. Oceans were thought of as passive containers, wide and deep, but geologically quiet. The Mariana Trench challenged that view completely. It showed that the oceans were not empty basins, but active participants in Earth's evolution, places where the crust bent, fractured, and descended back into the planet's interior. The Earth, it turned out, was alive with motion even in its darkest corners. Still, numbers alone were difficult to grasp. When scientists announced that the trench reached nearly 11 kilometers deep, the scale defied intuition. So they turned to comparisons. If Mount Everest were turned upside down and dropped into the trench, its summit would still lie more than a mile beneath the surface. The cruising altitude of a commercial airliner roughly matched the trench's depth. The Earth people realized was just as extreme downward as it was upward. Yet confirmation brought curiosity, not closure. What lived there, if anything? How did organisms survive such pressure? What did the water feel like, move like, behave like at those depths? And perhaps the most daring question of all, could a human ever go there? The discovery of the trench did not end the mystery. It opened it. Even today, despite high-resolution maps and decades of surveys, the Mariana Trench retains an aura of the unknown, partly because of its depth, partly because of its remoteness, and partly because knowing a place exists is very different from truly experiencing it. Mapped, but not yet touched, measured, but not yet visited. The deepest place on Earth had revealed itself. The next chapter would ask whether we could follow it down. Even that comparison only scratches the surface of what the numbers mean, because depth is not just distance. In the ocean, depth is pressure, and pressure is something we rarely feel directly in daily life. At sea level, the air presses gently against our bodies. We don't notice it because we've evolved within it. But water is far heavier than air. Every 10 meters you descend adds another atmosphere of pressure. By the time you reach the deepest point of the Mariana Trench, the pressure is more than 1,000 times greater than what you feel right now. That means every square inch of anything down there is being squeezed with the weight of several tons. Steel buckles, glass shatters, unprotected electronics collapse instantly. A human body without protection would not survive even a fraction of that descent. And yet, life does. This realization changed how scientists thought about the limits of biology. For a long time, it was assumed that extreme pressure combined with freezing temperatures and total darkness would make the deepest ocean sterile, a dead zone at the bottom of the world. But evidence slowly began to suggest otherwise. Even before humans ever visited the trench in person, samples brought up by dredges hinted at something astonishing: microscopic life, traces of organisms adapted to conditions once thought impossible. Life had not only reached the deepest place on Earth it had settled in. The question then shifted again. If life could survive, there could humans ever reach it safely? The idea seemed almost reckless. To descend 11 kilometers into the ocean meant building a vessel capable of withstanding pressures far beyond anything used before. Submarines designed for military or research purposes were built for a few hundred meters, perhaps 1,000. The trench demanded something entirely different. It required not just strength, but precision. A single weakness, a tiny flaw in design, could mean catastrophic failure. At that depth, there is no rescue, no margin for error. For years, the idea remained theoretical. Engineers sketched designs, scientists debated materials, funding came and went. The trench waited unchanged. Then, in the mid 20th century, one project moved from idea to reality, a vessel unlike any before it was conceived, not sleek or fast, but slow, heavy, and deliberately simple, a craft built not to roam the ocean, but to survive a single vertical journey into the deepest darkness on Earth. It would carry two people, just two, no room to walk, no room to escape. A steel sphere barely large enough to sit inside, suspended beneath a massive flotation tank. Every decision made in service of one goal: reaching the bottom alive. The descent would take hours, the ascent even longer, and for a brief moment at the very bottom, human eyes would finally look out onto a place that had existed for millions of years without ever being seen. But that moment still lay ahead. For now, the trench remained what it had always been: a silent presence beneath the Pacific, measured, mapped, and named, yet still untouched by human hands. A reminder that discovery is not the same as understanding, and that sometimes the most profound journeys are not across the surface of the world, but straight down into its deepest silence. Even the grandest things humans have ever built shrink into insignificance when set beside the depth of the abyss. Here on the surface, we live beneath a single atmosphere of pressure, the gentle, invisible weight of air resting on our bodies. It is so constant that we barely notice it. But beneath the ocean, that balance changes quickly. With every 10 meters of descent, the pressure increases, stacking layer upon layer of force. Divers feel it early, a tightening in the ears, a reminder that the body was never meant to linger there for long. At 100 meters, only the most carefully trained and equipped can survive. And at the bottom of the Mariana Trench, the pressure becomes almost unimaginable, more than 1,000 times greater than what we experience at sea level. It is the kind of force that could crush steel collapse hulls and erase empty spaces inside solid objects. And yet, even in this crushing world, life persists. Tiny organisms thrive, where logic says they should not exist. Instead of rigid skeletons, many have soft, flexible bodies that yield rather than resist. Their cells are stabilized by unusual chemistry, allowing them to function where pressure would destroy most forms of life. To them, the trench is not hostile or extreme. It is ordinary. It is home. For the human mind, however, the scale remains difficult to hold. One way to approach it is through time rather than distance. Imagine lowering a heavy object toward the seafloor, letting it sink steadily into the darkness. Even at a generous speed, it would take well over an hour to reach the bottom, more than an hour of uninterrupted descent passing through layers of water, colder, darker, and quieter than the last. During that time, the surface world above would continue moving, waves shifting winds, pushing the vessel far from its starting point. The trench is not just deep, it is slow. Reaching its floor is a journey measured as much in patience as in meters. Temperature completes the transformation. Sunlit waters near the surface can feel warm and alive, but far below the ocean settles into near freezing stillness. The water never turns to ice, held liquid by the immense pressure, but the cold is constant, draining heat and energy from anything exposed. It is a complete reversal of conditions, a descent from brightness into a realm where darkness and cold reign permanently. Scientists sometimes turn to land-based comparisons to make this scale clearer. The Grand Canyon, vast and overwhelming to stand beside, reaches depths of about 1.5 kilometers. The Mariana Trench plunges nearly 7 times farther. Imagine standing at the canyon's floor and stacking entire canyons upward one atop another until daylight finally appears. Even then, the trench remains difficult to fully imagine. Some places on Earth are not meant to feel familiar. They exist beyond instinct, stretching the limits of what we can truly picture. The sheer size of those numbers makes them difficult to picture clearly. Our minds tend to resist scales that stretch beyond everyday experience, and that resistance is part of what gives the trench its lingering sense of mystery. It sits right at the edge of what imagination can comfortably hold, and perhaps that is exactly how the deepest place on earth should feel. Not neat or easily understood, but vast, humbling, and slightly unreal. Yet the importance of scale goes far beyond abstract measurements. It directly shapes what exploration is even possible. Reaching the bottom of the trench demands technology built to survive forces far outside normal engineering limits. Every component must endure crushing pressure, near freezing temperatures, and total darkness, all while operating with no margin for error. There is no quick rescue, no easy return. Each attempt requires years of preparation, careful design, and resources available to only a few organizations in the world. This is why visits to Challenger Deep are so rare. The trench is not just deep in a physical sense, it is deep in commitment, in cost, and in risk. Its scale creates a natural barrier that few can cross. And yet, for all the ways it resists us, the trench also invites wonder. Knowing that such an extreme place exists here on our own planet quietly shifts perspective. We often imagine mystery as something distant, hidden among stars or orbiting other suns. But beneath the familiar surface of the Pacific lies a world just as alien, just as severe, and in many ways even less understood. It is often said that we know more about the surface of Mars than we do about the deepest parts of our own oceans. That comparison is not meant as exaggeration. It reflects how difficult the trench is to study not only because of its depth, but because of its immense size. The Mariana Trench is not a single pit or point. It is a sprawling system that stretches for more than 1,000 miles along the Pacific floor. Within it lie slopes, ridges, and hidden valleys, each shaped by different conditions. Challenger. Deep is simply the lowest known point within this larger scar. To truly understand the trench would require countless surveys, slow passes back and forth, with sonar assembling fragments of information into a picture that is still incomplete. Even satellites, which can estimate seafloor depth by observing subtle changes in gravity at the ocean's surface, offer only a rough outline. Much of the trench remains unresolved not because of neglect, but because its scale defies easy study. Those who speak of approaching the trench describe a profound sense of awe. The seafloor seems to tilt downward and then vanish, dropping into darkness with no visible end. That sensation of endlessness is not about numbers, but perception. Even when we know the depth is finite, the mind interprets such a descent as infinite because it exceeds anything we encounter in daily life. In this way, the scale of the Mariana Trench exists on two levels at once. It is a measurable reality defined by kilometers, miles, and pressure, and it is also a psychological experience, a confrontation with vastness that feels boundless. The trench stands as more than a geological feature. It is a symbol of the immensity still hidden within our world, a reminder that Earth holds places as challenging and mysterious as anything beyond it. Beneath the quiet surface of the ocean lies a realm shaped by forces we rarely feel, but that dominate everything below. And as we begin to understand that enormity, it becomes clear why pressure is such a defining presence in the abyss. For life, for exploration, and for the shape of the trench itself, the crushing weight of the ocean is the silent architect of everything that exists there. Once you begin to truly imagine the depth of the Mariana Trench, another realization naturally follows. All that water above is not just space or distance, it is weight. Every single drop has mass, and when unimaginable numbers of those drops are stacked into a column nearly 11 kilometers tall, the result is not just depth, but force. That force is pressure, and it transforms everything it touches. At the surface, pressure is so familiar that we rarely think about it at all. Right now, wherever you are, the air above you presses down with the weight of one atmosphere. It amounts to roughly 14 pounds on every square inch of your body. Added together, that force equals several tons. And yet you don't feel crushed because your body pushes outward with equal pressure from within. Life at the surface is balanced, adapted to exist comfortably beneath an invisible blanket of air. Even small changes to that balance are easy to notice. Anyone who has flown in an airplane has felt their ears pop as cabin pressure shifts. Anyone who has dived beneath the surface of a pool has felt a gentle squeeze in their sinuses after only a few meters. These sensations are mild, fleeting hints of what pressure truly is. They are reminders that force is always present, even when it feels harmless. Now imagine extending that descent far beyond a swimming pool or shallow dive. In the ocean, pressure increases steadily with depth. For every 10 meters you go down, another full atmosphere is added. At 10 meters, the pressure doubles. At 20, it triples. At 30, it becomes 4 times what your body experiences at the surface. For scuba divers, these changes quickly become serious. Breathing compressed air at depth alters how gases behave inside the body, and beyond certain limits, it becomes dangerous. This is why deep diving requires strict training, careful planning, and specialized equipment, even when descending only a small fraction of a kilometer. But the Mariana Trench does not stop at tens or even hundreds of meters. It continues downward for nearly 11 kilometers. At the bottom, the pressure is no longer measured in small increments. It reaches levels that are difficult to comprehend. More than 1,000 times the pressure at sea level presses inward from every direction. It is a force strong enough to crush unprotected steel, collapse solid structures, and erase empty spaces instantly. In that environment, pressure is no longer a background condition. It is the defining feature of existence itself. And yet, despite how extreme it sounds, pressure is not inherently violent. It is simply relentless. It does not strike or explode. It presses evenly and endlessly. In the trench, there is no sudden moment when pressure arrives. It builds gradually, layer by layer, meter by meter, until it becomes the dominant reality. Everything that exists there must be shaped by it, designed around it, or adapted to live within it. Understanding this helps explain why the Mariana Trench is so difficult to reach and so rare to visit. It is not just far away. It is a place where the very physics of everyday life no longer apply. Pressure dictates what materials can survive, how machines must be built, and how living cells must function. It is the invisible weight that defines the abyss, quietly shaping a world unlike anything on the surface. Put another way, the pressure at the bottom of the Mariana Trench is more than 1,000 times greater than what your body is experiencing right now. Scientists often rely on dramatic comparisons to make that number feel real, because without them, it remains almost abstract. They speak of elephants stacked one upon another, or dozens of fully loaded jumbo jets pressing down on a single spot. Imagine that kind of weight bearing down without pause. Steel would buckle, concrete would fracture. Submarines designed for conventional naval depths would be crushed almost instantly. At those depths, the ocean is not calm or neutral. It is an active force pressing inward from every direction with relentless intensity. Anything that descends into the trench must be engineered with one central purpose in mind: to resist that pressure, or to yield to it in just the right way. And yet, in the midst of this crushing environment, life persists. This is perhaps the most astonishing truth of all. What humans see as an extreme, hostile abyss requiring extraordinary technology simply to visit for a few hours is, for some organisms, a perfectly ordinary home. Over millions of years, evolution has shaped living forms that are not hardened against pressure, but adapted to exist within it. Many deep sea creatures lack rigid skeletons or brittle shells that would snap under stress. Instead, their bodies are soft and flexible, able to compress without breaking. At the microscopic level, their cell membranes are reinforced with special compounds that keep them stable under immense force. The proteins inside their cells, the delicate machines that drive life, are chemically tuned so they do not unravel when squeezed beyond what surface life could endure. In some cases, species found in the trench are so finely adapted to these conditions that they cannot survive at shallower depths where pressure is lower. What seems intolerable to us is essential to them. The trench reveals something important about life itself. It is not as fragile as we often assume. It is resilient, inventive, and capable of persisting even where physical forces appear overwhelming. For biologists, this realization reaches far beyond the ocean. If life can thrive under thousands of atmospheres of pressure, in total darkness and near freezing temperatures, then similar life might exist beneath the icy crusts of distant worlds, in hidden oceans, on moons like Europa or Enceladus. The Mariana Trench, in this way, becomes more than the deepest place on Earth. It becomes a quiet lesson about possibility, showing us that life's limits may be far wider than we once believed. At extreme depths, like the Mariana Trench sound, becomes one of the few ways information can still move. Light disappears within the first few hundred meters of the ocean swallowed by water long before reaching the abyss. But sound, shaped and carried by pressure, can travel astonishing distances. In the deep sea, the ocean itself acts like a vast acoustic tunnel, guiding vibrations through layers of compressed water. Whales and other marine animals rely on this property, sending calls that can cross entire ocean basins. Even at the bottom of the trench, faint echoes from distant storms or shifting ice can sometimes be detected, arriving as low, distant murmurs rather than sharp noises. For human explorers, this means the deep ocean is never completely silent, but its sounds are subtle and unfamiliar. Submersibles descending into the trench often record a quiet hum punctuated by the creak of metal adjusting to pressure, the soft hiss of systems working, and occasionally the distant rumble of geological movement. Earthquakes, landslides, and tectonic shifts all send vibrations through the water, reminding us that the planet is active, even in places that seem frozen and still. This acoustic world has helped scientists study the trench without always going there physically. By listening carefully, researchers can track underwater earthquakes, monitor plate movement, and even detect changes in deep currents. In a place where direct observation is difficult and dangerous, sound becomes a form of sight. It allows humans to sense what cannot be seen, to map the unseen contours of the abyss, and follow processes unfolding miles below the surface. The strange relationship between pressure and sound also affects the creatures that live there. Many deep-sea animals are thought to be sensitive to vibrations rather than light. Some have reduced or absent eyes, while others possess sensory systems tuned to detect subtle movements in the water. In total darkness, awareness comes not from vision, but from feeling. The trench is not a silent void, but a place where information moves in slow waves, carried by pressure and water rather than light. As we drift deeper into understanding the Mariana Trench, it becomes clear that pressure shapes everything. It shapes the bodies of animals, the tools humans build, the rocks beneath the seafloor, and even the way sound travels through the ocean. Pressure defines what is possible and what is not. It draws a boundary between the familiar surface world and the alien realm below. And yet, despite this boundary, the trench remains connected to the rest of the planet. Currents link it to the open ocean. Tectonic forces tie it to volcanoes and earthquakes felt far away. Even human activity, surprisingly, has left traces there, carried downward through sinking debris and microscopic particles. The deepest place on Earth is not isolated. It is woven into the same global systems that shape weather, climate, and life above the waves. For now, as we pause at this depth in our journey, it is enough to sit with the idea of pressure not as something abstract, but as a constant presence, a force that presses from all sides, invisible but absolute. In the Mariana Trench pressure is the ocean itself reminding us of scale of limits and of the quiet power that exists beneath the surface of our everyday world. In the absolute darkness of the Mariana Trench, bioluminescence becomes more than a curiosity. It becomes a language. Without sunlight, without shadows or horizons, many deep-sea creatures create their own signals. Brief pulses of living light that flicker and fade in the black water. These flashes may lure prey, confuse predators, attract mates, or simply announce presence in a world where sight would otherwise be impossible. What looks like beauty to us is survival to them. Chemistry turned into communication. Some organisms glow steadily, others in sudden bursts. Certain species use light to hide rather than reveal themselves, matching the faint glow from above so predators below cannot see their silhouettes. Others emit light from specialized organs, carefully controlled, switched on only when needed. In the trench, light is precious. It costs energy to produce, so it is used with purpose. Every glow has meaning, even if we do not yet fully understand it. For humans descending into this darkness, the effect is profound. Submersibles rely on artificial lights that cut narrow tunnels through the black, illuminating only small patches of the seafloor at a time. Beyond the reach of those beams, nothing exists visually. No distance, no edges, just darkness. Explorers describe the sensation as disorienting, as if space itself has collapsed around them. Up and down lose meaning. Time feels stretched, without sunrise or sunset, without visual reference points, the mind floats. And yet within that darkness, movement continues. Sediments drift slowly downward, like underwater snow. Tiny organisms pulse with faint light. Larger creatures pass through the beams briefly, then vanish. The trench is not empty. It is simply hidden. Its life unfolds quietly, adapted not only to pressure and cold, but to the absence of light itself. Darkness also preserves. Without sunlight, chemical reactions slow. Organic matter decomposes differently. The trench becomes a kind of archive where traces of life particles from the surface and even signals from distant geological events settle and remain. In this way, the darkness is not just a lack, but a condition, one that shapes how time moves, how matter behaves, and how life persists. When we think of the Mariana Trench, it is tempting to imagine it as hostile, lifeless, or empty. But the reality is more subtle. It is a world finely tuned to extremes, shaped by pressure and darkness in equal measure. A place where light is rare, but life has learned to create it. Where silence dominates, yet information still travels. Where human senses fail, but nature continues calmly, patiently, exactly as it has for millions of years. And as we continue drifting through this unseen world, it becomes clear that darkness in the trench is not the end of experience. It is simply a different beginning. When something cannot be seen, the mind fills the space for it. Darkness invites imagination, and the deeper the darkness, the more powerful those imagined shapes can become. This is why the trench has always carried a sense of unease, not because it is violent or chaotic, but because it is hidden. The unknown has a way of amplifying fear even when nothing threatening is present. In reality, most of the creatures living in the trench are small, slow, and cautious. They conserve energy, moving only when necessary. Food is scarce, drifting down from the surface in tiny particles known as marine snow. In the absence of light, there are no plants, no photosynthesis, no green foundation to the food chain. Everything depends on what falls from above or on chemical energy released from the earth itself. Life here is patient. Nothing is wasted. This scarcity shapes behavior. Many trench organisms grow slowly and live long lives. Some may take years to reach maturity. Others reproduce infrequently, releasing eggs or larvae that drift upward before settling back down. In such an environment, rushing would be fatal. Efficiency becomes survival. Every movement, every glow, every chemical signal has purpose. For human observers, this creates a strange contrast. The trench feels dramatic, extreme, overwhelming. But to the life that inhabits it, the abyss is stable. Pressures remain constant. Temperatures barely change. There are no storms, no seasons, no sudden shifts between day and night. In some ways, it is more predictable than the surface world. What feels hostile to us is simply normal there. This difference in perspective is important. It reminds us that extreme is a relative term. The trench is extreme only because we are not built for it. For the creatures that evolved there, it is the safest place they know. In fact, bringing them toward the surface can be deadly. As pressure decreases, their bodies can no longer function properly. Their cells fail, their chemistry breaks down. The surface, not the abyss, becomes the hostile environment. Darkness, then, is not emptiness. It is not absence. It is a condition shaping life in quiet, precise ways. The trench does not need light from the sun because it has learned to exist without it. And as we drift deeper into understanding this world, the fear that once filled the darkness slowly gives way to something else: respect, awe, and a calm realization that life once started is remarkably difficult to extinguish. The Mariana Trench is not a void. It is a hidden ecosystem operating beyond our senses, following rules older than humanity itself. And the longer we listen rather than look, the more that silent world begins to feel less frightening and more deeply alive. Some of these sounds repeat with steady patterns, while others appear once and never again. Scientists listening through hydrophones describe them as haunting rather than frightening low moans that rise and fade, sharp clicks that echo briefly, and distant roars that feel more geological than biological. Many originate far from the trench itself. A storm thousands of kilometers away, waves crashing along a distant coastline, or ice shifting near the poles can all send vibrations traveling through the deep ocean. The trench, in this sense, becomes a receiver collecting echoes from across the planet. This means the Mariana Trench is never truly silent. Even in total darkness, it is filled with information. Sound carries stories of movement, stress, and change happening far beyond the abyss. An earthquake along a tectonic boundary announces itself long before any surface sensor notices. A collapsing slope on the trench wall sends a low frequency tremor through the water. The planet is constantly speaking, and the deep ocean is always listening. For the creatures that live there, sound may be as meaningful as light is to us. Vibrations can signal danger, the presence of food, or the movement of another organism nearby. In a world without vision, even the smallest disturbance matters. A shift in pressure, a faint pulse, a ripple through the water. Survival depends on sensitivity rather than speed. For humans, this auditory world changes the way exploration feels. Inside a submersible, explorers often report that the darkness feels complete, but the sounds make the space feel alive. The creak of the vessel adjusting to pressure, the hum of instruments. Occasionally, an external noise picked up by sensors and translated into something audible. These sounds remind those inside that they are not alone, even in the deepest place on Earth. The trench teaches an important lesson here. Absence of light does not mean absence of activity. Silence does not mean stillness. Much of what happens on our planet occurs beyond our senses, in realms shaped by forces we rarely experience directly. The Mariana Trench is one of those realms operating on rules that feel foreign only because we are visitors. And as we continue this slow descent through understanding, another realization begins to form. Darkness, pressure, and silence are not barriers to life. They are conditions. And life, once given time, adapts not by resisting those conditions, but by weaving itself into them. In the deepest ocean, existence becomes quieter, slower, and more deliberate. There is no rush, no wasted movement, no excess. Everything that survives there does so because it fits perfectly into the narrow margins allowed by the abyss. The trench is not chaotic. It is finely balanced. From here, it becomes natural to ask not just how life survives in the Mariana Trench, but what kind of life it is. What forms emerge when evolution is shaped by crushing pressure, endless night, and near silence? What does a creature look like when speed is unnecessary and patience is everything? That is where our journey leads next. In the deep ocean, sound does not fade the way it does at the surface. Instead, it travels vast distances, bending through layers of pressurized water and arriving far from its source. A noise created hundreds or even thousands of miles away can reach the bottom of the Mariana Trench, faint but still recognizable. Storms on the surface announce themselves long before they pass overhead. Rain striking the Pacific creates a soft, continuous hiss that drifts downward. Thunder rolls through the water like distant drums. Powerful waves from hurricanes send low vibrations that sink deep into the body of the ocean. From the perspective of Challenger Deep, the surface is never truly quiet. It is constantly alive with distant motion translated into sound and carried downward like an echo of the world above. Alongside these signals from far away are the sounds of life itself. The deep sea is not silent. Many creatures communicate through clicks, pulses, and low vibrations. Some shrimp create sharp snapping sounds. Certain fish generate rhythmic drumming by vibrating internal organs. Even in total darkness, life makes itself known. For animals that cannot rely on sight, sound becomes essential. It reveals movement, proximity, danger, and opportunity. Every faint click or rumble is part of an ongoing conversation unfolding in the dark. When scientists first began listening to recordings from the trench, they were surprised by the richness of what they heard. They had expected emptiness, perhaps the occasional groan of shifting rock. Instead, they encountered complexity, layers of sound overlapping and interacting. The abyss was not a void. It was active, connected, and responsive. The trench, though hidden from view, was deeply linked to the rest of the planet. Every earthquake, every storm, every migrating creature left traces in its waters. Not all of these sounds are natural. Human activity reaches down as well. Ships crossing the ocean send vibrations from engines and propellers into the depths. Sonar pulses used for navigation or military purposes echo through the water and appear in hydrophone recordings. Even here, in the deepest place on Earth, the influence of civilization can be detected. Scientists often note how much of the acoustic environment can be traced back to human presence, a reminder that no part of the ocean is completely untouched. And then there are the sounds that remain unexplained. Unusual whistles, low moans, and unfamiliar tones that do not immediately match known animals or geological processes. Some mysteries are eventually solved. A sound once thought unknown may later be identified as a whale call, another traced to ice shifting far from the tropics. But some recordings still resist clear explanation. These lingering questions are part of what keeps deep sea research alive. They remind us that the ocean still holds secrets, not only in its darkness, but in its voice. One of the most striking aspects of listening to the trench is how it collapses distance. A single hydrophone, which has a place at the bottom, may capture an earthquake near Japan, a storm near Hawaii, and a whale call from far to the north, all within the same stretch of recording. The abyss becomes a meeting place for signals from across the globe. In that sense, the Mariana Trench is like an ear pressed against the earth itself, quietly receiving whispers from every direction. For those who have descended in submersibles, sound takes on a different meaning. Inside the sealed vessel, external noises are muted, but the structure itself speaks. The hull creaks and adjusts as pressure increases each sound, a reminder of the immense force surrounding them. In that environment, even the smallest noise feels amplified by awareness. Every creak carries weight. Every vibration is noticed. It is an experience that blends awe with vulnerability, a quiet reminder of just how thin the barrier is between human technology and the crushing depth outside. Outside the submersible, everything feels silent to the human ear, but through sensitive instruments, the water reveals itself as alive with information. For those inside the vessel, it can feel as though one sense has been taken away and replaced by another. Vision becomes limited, but sound expands. It is a reminder that perception today is not fixed. It depends entirely on the environment and on the tools we use to experience it. The science of listening to the trench is still in its early stages, yet it has already shown something remarkable. Even at the deepest point on Earth, the ocean is not isolated. It is woven into a global network of motion and energy, its waters gently vibrating with the distant memory of storms, earthquakes, living creatures, and human activity. What seems like silence is not emptiness at all. It is a space filled with echoes. When people imagine alien life, they often think of distant planets, hostile surfaces, strange skies, and creatures unlike anything familiar. But in truth, one of the most alien environments imaginable exists right here on Earth. The deep ocean, and especially the Mariana Trench, has produced forms of life so unfamiliar that they feel as though they belong to another world. Scientists often compare deep sea research to space exploration, not just because both push technology to its limits, but because the organisms found there challenge our assumptions about what life should look like. One of the most striking differences between trench life and surface life is appearance. Sunlight shapes almost everything we see on land. Colors, patterns, and camouflage all depend on light. In the abyss, sunlight never arrives, and so those visual rules no longer apply. Many deep sea creatures are nearly transparent, their bodies like drifting glass. Others are pale, almost colorless, reflecting nothing because there is no light to reflect. In this darkness, color loses its meaning. Instead, light is produced from within. Bioluminescence is so widespread in the deep ocean that it functions almost like a substitute for sunlight. Soft blue glows, brief green flashes, and occasional red pulses appear and disappear in the black water. Some organisms glow constantly, others blink in coded patterns, and some release light only in moments of stress or opportunity. To a human observer, it can resemble a slow moving sky of underwater stars. Among the most famous examples is the anglerfish, whose glowing lure extends from its head like a living lantern. In total darkness, that small point of light becomes irresistible. Tiny crustaceans and fish drift closer, drawn by curiosity or confusion, until they are suddenly consumed by a mouth lined with long, inward pointing teeth. The anglerfish appears monstrous by surface standards, but in the trench it is perfectly adapted. Its large mouth allows it to seize rare meals whenever they appear. Its expandable body lets it survive long periods without food. What looks frightening to us is simply efficiency shaped by scarcity. In the Mariana Trench, life is not built for beauty as we define it. It is built for survival under pressure, darkness, and silence. Every form reflects the environment that shaped it, and in that sense, these creatures are not strange mistakes of nature. They are precise answers to extreme conditions, living proof that evolution can sculpt light to endure almost anywhere. Not all light in the trench is used to hunt. Some creatures use it to disappear by producing a soft glow along their undersides that closely matches the faint light filtering down from above. They erase their own silhouettes. This strategy, known as counter illumination, allows them to blend seamlessly into the darkness. To a predator watching from below, there is nothing to see. In this way, light becomes camouflage rather than attraction. Other species use brief flashes as signals calling to potential mates or warning rivals to keep their distance. In the abyss, light is not decoration, it is information, a quiet language written in pulses and glimmers, essential for survival in a world without dawn or dusk. Beyond bioluminescence, many trench creatures feel alien because of their proportions. Freed from the familiar constraints of surface life bodies, evolve in unexpected ways. Some animals develop enormous eyes, capable of capturing even the faintest glows, while others abandon vision altogether. Giant squid drift through the dark with eyes as large as dinner plates, scanning vast volumes of black water. Gulper eels open mouths so wide they seem impossibly oversized for their narrow bodies, ready to seize any rare opportunity for food. The blobfish, often misunderstood, appears misshapen only when brought to the surface. In its natural environment, its soft structure is perfectly balanced against immense pressure. What looks strange to us is simply what works down there. Size itself behaves differently in the deep. Some organisms shrink, surviving on minimal energy and scarce resources. Others grow unexpectedly large. Colossal squid and oversized amphipods found in trenches dwarf their shallow water relatives. This pattern, sometimes called deep sea gigantism, is still debated. Slower metabolisms, reduced predators, cold temperatures, and high pressure may all play a role. Larger bodies may conserve energy more efficiently in an environment where meals are rare and unpredictable. The result is a collection of forms that feel exaggerated, almost unreal, as though shaped by a set of rules entirely separate from the surface world. And beneath all of this visible life lies something even more fundamental: microbes. Vast communities of microscopic organisms live within the sediments, the rocks, and the water itself. They do not depend on sunlight. Instead, they draw energy from chemical reactions, feeding on methane, hydrogen, sulfur, and other compounds rising from the earth below. This process, known as chemosynthesis, supports entire food webs in total darkness. Many of these microbes are extremophiles adapted to pressure, cold, and chemical conditions that would destroy most known life. For scientists, these microorganisms may be the most important inhabitants of the trench. They show that life does not require warmth, light, or gentle conditions. It requires only energy and time. To astrobiologists, the trench becomes more than a deep sea curiosity. It becomes a guide. If life can flourish here, beneath kilometers of water and crushing pressure, then perhaps it can also exist beneath the icy shells of distant moons or in the hidden oceans of other worlds. In this way, the Mariana Trench is not just a destination on Earth, it is a window into the possibilities of life across the universe. For many people, simply seeing images of creatures from the trench is enough to stir both awe and discomfort. Their translucent bodies, oversized mouths, and faintly glowing patterns feel distant from anything in everyday life. Yet to label them as monsters is to misunderstand them. In their world, they are not strange at all. We are. Creatures dependent on sunlight, air, and delicate conditions would seem impossibly fragile by comparison. Their apparent oddness is not a flaw in nature, but a mirror reflecting our own unfamiliarity. Explorers who encounter these animals directly often describe the moment as dreamlike. From inside a submersible, beams of light cut through the darkness and unfamiliar forms slowly emerge. Some drift lazily, conserving precious energy. Others move with sudden speed, taking advantage of a rare chance to feed. A softly glowing shrimp like animal may pass by. A fish with nearly transparent skin might hover just beyond the light. It feels like watching life from another planet. And then the realization settles in. This is not another world. It is our own revealing forms of life that have always existed beyond our reach. The diversity is astonishing. Scientists believe we have identified only a small fraction of deep sea species. Almost every expedition brings back something new, sometimes organisms so distinct they form entirely new branches on the tree of life. Robotic submersibles have filmed enormous ribbon-like siphonophores stretching through the dark jellyfish, pulsing like living lanterns, and gelatinous shapes that defy easy classification. Each discovery reinforces the idea that the trench is not an empty void, but a complex, active ecosystem still largely unknown. Food in this environment is scarce, and that scarcity shapes everything. Most energy arrives as marine snow, a slow, constant fall of organic debris drifting down from the surface. Tiny fragments of dead plankton, bits of algae, and the remains of larger animals descend through the water column, sometimes taking weeks to reach the bottom. In the trench, this steady snowfall is invaluable. Creatures filter it, collect it, and compete for it. Some are scavengers, drawn quickly to the rare event of a whale or large fish sinking to the depths. Others feed indirectly, consuming bacteria that break down organic matter. Nothing is wasted. Every particle is part of a carefully balanced system built on patience and efficiency. Despite these limitations, the trench supports remarkable abundance. Microbial life thrives in the sediments, reaching staggering densities. Amphipods gather rapidly around bait lowered by researchers emerging from the darkness in surprising numbers. Fish patrol the slopes perfectly adapted to pressures that would instantly destroy surface-dwelling species. This quiet abundance speaks to life's resilience. Even without light, with minimal food and overwhelming pressure, life does more than persist. It adapts, organizes, and flourishes. For humans, studying trench life offers more than scientific insight. It reshapes perspective. We often think of forests, grasslands, birds, and mammals as the default expression of life on Earth. But in reality, much of the planet's biosphere looks nothing like that. The inhabitants of the trench remind us that life is not confined to familiar shapes or conditions. It is flexible, resourceful, and endlessly inventive. Seen this way, the trench is not just a deep place, it is a lesson, a reminder that our definitions of normal are narrow, shaped by where we happen to live. Beneath the surface in darkness and pressure, life has followed a very different path, one just as valid and just as ancient. Once you accept that these creatures exist, glowing, drifting, and feeding as silence, far below, a new question naturally arises. How did humans ever manage to reach them at all? How did we descend into that black, pressurized world to witness it firsthand? By the mid 20th century, the Mariana Trench had moved from myth into measured reality. Sonar surveys confirmed its staggering depth. Expeditions traced its contours. Scientists agreed that Challenger Deep marked the lowest known point on Earth. But knowledge alone was never enough. Curiosity kept pressing forward, asking not only how deep it was, but what it was like to be there, and whether humans could ever reach it. For centuries, such a journey had been unimaginable. But by the late 1950s, technology had finally caught up with ambition. The vessel chosen for this unprecedented descent was called Trieste, a bathyscaphe designed in Switzerland and later acquired by the United States Navy. The word bathyscaphe comes from Greek roots meaning deep and ship, and Trieste was built with one purpose in mind: to survive where nothing else could. Trieste looked nothing like a conventional submarine. Instead of a sleek hull, it consisted of a large buoyant float filled with gasoline with a massive steel sphere suspended beneath it. The float provided lift, while the sphere served as the crew compartment. That sphere, only a few meters wide, was constructed from steel more than 12 centimeters thick, carefully engineered to withstand pressures far beyond anything humans had ever experienced. Inside, there was room for just two people. In January of 1960, those two were Jacques Piccard, a Swiss engineer and oceanographer whose father had helped design the craft, and Don Walsh, a U.S. Navy lieutenant. Together they prepared to attempt something no one had ever done before: descend nearly 11 kilometers to the bottom of Challenger Deep. On the morning of January 23, 1960, Trieste was towed into the Pacific near Guam. The gasoline-filled float above the sphere ensured buoyancy, while tons of iron pellets served as ballast. By releasing or holding this ballast, the crew could control their descent and ascent. The system was simple, relying on gravity and buoyancy rather than engines, a deliberate choice in such an extreme environment. Piccard and Walsh climbed into the steel sphere through a narrow hatch and sealed themselves inside. The space was cramped, barely large enough to sit. The air quickly became warm and humid. Oxygen supplies were limited, and carbon dioxide scrubbers worked continuously to keep the atmosphere breathable. Outside communication relied on radio, though signals weakened as they sank deeper. With final checks complete, the descent began. At first, the journey downward felt almost gentle. Ballast pulled them steadily Through the upper layers of the ocean, sunlight faded quickly, turning from blue to darkness. Outside the viewports, only drifting particles occasionally passed through the beam of their lights. Minutes blurred into hours as they continued to sink. All the while, pressure increased relentlessly. Inside the sphere, the men were protected, but the ocean pressed inward with unimaginable force. The dominant sounds were mechanical, the subtle groaning of the hull as it adjusted, the faint crackle of radio static, the quiet hum of instruments. Then, at around 9,000 meters below the surface, something went wrong. One of the outer plexiglass viewports fractured under the strain. A sharp bang echoed through the sphere, jolting both men in the darkness. But the inner window and the steel sphere held. With no way to turn back, they continued downward, fully aware of how narrow the margin for survival had become. At depths where pressure exceeded 1,000 atmospheres, even a minor failure could mean instant catastrophe. Still, they pressed on. The descent lasted nearly 5 hours. Imagine sitting inside a steel capsule while kilometers of ocean stack above you, the weight increasing second by second. Outside, there was no light at all. The sensation was not of falling, but of sinking endlessly, drifting deeper into a world that could not be seen. Eventually, the depth gauge approached 11,000 meters. Trieste had reached Challenger Deep. What awaited them at the bottom was unexpected. Instead of jagged rock or dramatic formations, the seafloor appeared flat and soft, blanketed in fine, pale sediment. The water, illuminated only by their lamps, was clearer than anticipated. And then came the most surprising sight of all. They observed signs of life. Small fish resembling flatfish or sole moved slowly across the mud. Their presence overturned long-held assumptions that complex life could not exist under such crushing pressure. Picard later described the scene as an endless plain of beige mud stretching beyond the limits of visibility. Walsh recalled it as simple and featureless, yet unmistakably alive. They remained on the bottom for only about 20 minutes. Instruments recorded temperature and pressure. The men took in what they could through the small viewports, fully aware that no human eyes had ever seen this place before. Then they released ballast and began the long ascent. The return to the surface was quicker, taking roughly 3.5 hours. As iron pellets dropped away, Trieste became buoyant and slowly rose through the darkness. After nearly 9 hours underwater, the vessel finally broke the surface. Picard and Walsh emerged exhausted, cramped, and shaken, but alive. They had reached the deepest point on Earth and returned to tell the story. The Trieste dive stands as one of the great milestones in human exploration. In many ways, it was the ocean's equivalent of the first lunar landing. Just as astronauts set foot on another world, Picard and Walsh descended into the planet's deepest abyss. Their journey proved that technology could withstand the immense pressures of the trench, if only briefly. It also confirmed that life persists even in the most extreme environments imaginable, and yet despite its success, no human would repeat the feat for decades. The costs were high, the risks enormous, and Trieste itself was eventually retired and preserved as a historic artifact. Once again, the trench slipped back into silence, visited only by robotic explorers drifting through the darkness. For the two men who made the journey, the experience never faded. Walsh later described it as both terrifying and deeply humbling a visit to a world utterly unlike the surface. Picard viewed it as a triumph of curiosity and engineering. Together, they demonstrated that the abyss was not unreachable. Whenever the Mariana Trench is mentioned today, the Trieste dive is always remembered. It marked the first moment when Challenger Deep was not merely measured, but directly experienced by human beings. That moment closed the distance between centuries of imagination and direct human experience. What had once belonged to myth, guesswork, and speculation was now confirmed by sight. The deepest place on Earth was no longer unreachable. It was real, visited, and briefly inhabited by human presence. From that point on, the trench was not only an idea, but a place. The name Challenger Deep carries both history and weight. It is more than a label on a chart or a figure in a data table. It represents the ocean at its absolute extreme. The name traces back to HMS Challenger, the British research vessel that sailed in the 1870s on the first true global scientific expedition of the deep sea. That voyage laid the foundations of modern oceanography. When its early measurements hinted at an unusually deep region in the western Pacific, the connection was set. Years later, as improved technology confirmed the depth, the deepest point was formally named Challenger Deep, honoring the ship that first pointed humanity in that direction. Challenger Deep is not a single pinpoint or narrow pit. It is a small region near the southern end of the Mariana Trench, containing several basins spread across tens of kilometers. Each basin reaches staggering depths, and which one is deepest depends on how and when it is measured. Together, they form the lowest known places in Earth's crust, the ultimate downward bend where the Pacific Plate slips beneath the Mariana Plate. To imagine Challenger Deep requires the reversal of perspective. On land, we are used to looking up into distance, into sky and space. But at the bottom of the trench, distance presses downward instead. Above is not open air, but kilometers upon kilometers of water stacked overhead, heavy and unyielding. The separation from the surface is so vast that even the tallest mountain on Earth would vanish within it. There is no sense of openness, only depth. Not light above, but mass. Not emptiness, but weight. For scientists, Challenger Deep is compelling, not just because it is the deepest point, but because it is a place where the planet itself is actively reshaping. The trench exists due to subduction, a slow but relentless process in which the massive Pacific Plate is forced beneath the smaller Mariana Plate. Here, that motion reaches one of its most extreme expressions. The seafloor bends downward into the mantle, dragged by forces operating far below human perception. Earthquakes originate from this grinding contact. Volcanoes rise in nearby island chains, fueled by molten material created as the descending plate heats and melts. Challenger Deep is not a static scar. It is a living boundary shaped continuously by geological power. Yet geology is only one layer of the story. Against every intuitive expectation, Challenger Deep is also a functioning ecosystem. Life persists in sediments and waters where pressure is immense and sunlight non existent. Microbes thrive by feeding on chemicals released from rock and organic debris. Amphipods swarm to scarce food sources, scavenging what little reaches the bottom. Fish patrol the muddy seafloor, pale and pressure adapted, perfectly suited to conditions that would destroy surface life instantly. The deepest point on Earth is not empty. It is quiet, dark, and compressed, but it is alive. A hidden world operating beyond human comfort, yet entirely part of our planet. Challenger Deep stands as proof that extremes do not mean absence, and that even at the very limits of depth, Earth continues to host complexity, motion, and life. For biologists, this is precisely what makes Challenger Deep so remarkable. It demonstrates that life is not limited to gentle environments or narrow comfort zones. Instead, it pushes outward into extremes, into crushing pressure and permanent darkness, into regions once assumed to be sterile and unreachable. Challenger Deep expands our understanding of what life can tolerate, and more importantly, where it can exist. Humanity's relationship with Challenger Deep has always carried a sense of tension. On one level, it represents the ultimate downward destination, the farthest point we can descend without leaving our planet. On another, it remains almost entirely inaccessible. Only a very small number of people have ever reached it. The historic descent of Trieste in 1960 marked the first. Decades later, filmmaker James Cameron followed in a solitary dive aboard Deep Sea Challenger. Since then, only a handful of additional missions have visited the bottom, some crewed, most robotic, each exploring only tiny fragments of the seafloor. In total, fewer than 30 people have ever been to Challenger Deep, a number smaller than those who have walked on the moon. That rarity gives the place a unique symbolic weight. Challenger Deep is not just a location on Earth, but a threshold. To reach it is to sit inside a narrow shell of steel at the absolute boundary of human oceanic exploration. Beyond it, there is nowhere deeper to go. In that sense, it mirrors space itself. Astronauts push outward into vast emptiness, while deep sea explorers descend into compressed darkness. One journey reaches toward infinity, the other toward an extreme limit. Both define the edges of human reach. Even the depth of Challenger Deep resists precise definition. Different expeditions have measured it at slightly different values, usually between about 10,900 and 11,000 meters. These variations are not errors so much as reflections of the difficulty involved. Measuring depth at such extremes depends on sound waves traveling through water whose temperature and salinity subtly affect their speed. Satellites can estimate depth indirectly by detecting gravitational effects on the sea surface, but those methods lack fine detail. Sonar provides greater accuracy, yet even then, exact numbers shift by a few meters. The deepest point on Earth remains known, but not pinned to a single perfect figure. That uncertainty only deepens its mystique. For those who have actually reached the bottom, Challenger Deep is often described as visually unremarkable. There is no dramatic chasm or jagged cliff. Instead, the seafloor appears flat and quiet, coated in fine beige sediment that has settled slowly over millions of years. Many explorers are surprised by its simplicity. Expectations of drama give way to stillness, and yet that simplicity is precisely what makes the experience profound. To look out at an ordinary muddy plain and know that you are deeper than any other human being has ever been is a realization that carries immense weight. The landscape itself may be plain, but its context transforms it into something extraordinary. Challenger Deep is not defined by spectacle, but by position. It is the absolute bottom of the known world, a place where Earth reaches its lowest point and quietly continues unshaped by pressure time and life adapting beyond our imagination. Places like this almost inevitably gather symbolism around them. Mount Everest, the highest point on land, draws climbers from around the world, pulled by the idea of standing closer to the sky. Challenger Deep. The lowest point is its quiet counterpart. One points upward, the other downward. One rises into thin air, the other sinks into crushing darkness. Both represent extremes, and both attract those who feel compelled to test the limits of what is possible. The difference is striking. Everest is climbed by hundreds of people each year. Challenger Deep, by contrast, remains accessible to only a handful. It cannot be reached by endurance or strength alone. It demands technology, engineering funding, and an acceptance of extraordinary risk. Perhaps that inaccessibility is what gives it such power. It has not been claimed or normalized. It resists familiarity, and so it retains its mystery. In the public imagination, Challenger Deep often becomes a stage for speculation. Writers and filmmakers cast it as a place where monsters might hide or secrets might wait in silence. The reality is far quieter, yet no less astonishing. Its wonder does not come from imagined creatures, but from what actually exists there. Microbes thriving under unimaginable pressure, amphipods feeding in near stillness, geological forces slowly reshaping the planet, and on rare occasions, humans descending briefly into that environment, aware that they do not belong there. Even the name carries a kind of poetry. Challenger Deep. It speaks of difficulty and depth of effort and unknowns. It reminds us that exploration is never passive. It is always a challenge, always a movement toward what lies beyond ordinary comprehension. The pairing of those two words captures the spirit of ocean science itself, a balance between technical struggle and quiet awe. That symbolic pull did not fade after the Trieste dive in 1960. Decades passed, yet the deepest point on Earth continued to call to explorers. When James Cameron descended alone in 2012, it was Challenger Deep that drew him. He wanted more than measurements. He wanted direct experience, to see the seafloor with his own eyes, to record it, and to bring back impressions rather than just data. For him, as for others, before him, the name itself felt like an invitation. In that sense, Challenger Deep is not merely a geographic feature, it is an unfolding story. Each expedition adds a few more lines, a clearer image, a deeper understanding. But the essence remains unchanged. It is the lowest point on the planet, the end of downward travel, a place where geology, biology, and human curiosity intersect. Its flat, unremarkable mud floor carries a significance far greater than its appearance suggests. For more than 50 years after the Trieste reached the bottom, Challenger Deep saw no human visitors. Machines descended, sonar mapped, instruments recorded, but no one looked out through a viewport at the deepest place on Earth after Jacques Piccard and Don Walsh returned to the surface in 1960. During that same span of time, astronauts walked on the moon, probes traveled to distant planets, and technology transformed daily life. Yet the deepest point on our own world remained untouched by human presence. That contrast fascinated James Cameron, a filmmaker whose work had long been shaped by both imagination and exploration. He was drawn to places that sat at the edges of experience. His films built vast worlds, from alien oceans to futuristic cities, but they were often rooted in a desire to explore real extremes. The Abyss, released in 1989, reflected his fascination with deep sea environments and the possibility of hidden life below. Titanic was inseparable from his personal dives to the wreck itself. For Cameron, filmmaking and exploration were never separate pursuits. They were expressions of the same impulse to go where few had gone to witness directly, rather than imagine from afar, and to return with stories that could bring others along. Challenger, deep, silent, and inaccessible, for half a century represented the ultimate expression of that drive. When the chance finally came to build a new vehicle capable of reaching Challenger Deep, Cameron committed fully. The project demanded years of careful design testing and engineering. This time, the approach was entirely different from Trieste. Instead of a heavy steel sphere hanging beneath a buoyant float, the new submersible named Deep Sea Challenger was long, narrow, and vertical, more like a green needle than a traditional submarine. It was designed for a single pilot, which meant Cameron would make the descent completely alone. Its construction pushed the limits of existing technology. Buoyancy came not from gasoline, but from advanced syntactic foam packed with microscopic hollow spheres strong enough to resist the immense pressure of the deep. At its core was a compact steel pressure chamber barely large enough for Cameron's body, surrounded by control screens and life support systems. Mounted on the exterior were high-definition cameras, sampling tools, and robotic arms, all designed to function in a place where pressure exceeds 1,000 atmospheres. On March 26, 2012, near the Mariana Islands, the dive began. Cameron entered the submersible early in the morning, the hatch sealed above him, and the vehicle was gently lowered into the Pacific. As the descent started, daylight faded quickly. Blue turned to gray, then to complete darkness. Hours passed as the sub slipped deeper layer by layer into the ocean. Cameron later described the sensation as less like diving and more like leaving Earth altogether, as if gravity itself were pulling him toward another world. Communication with the surface was slow and limited, reduced to brief text messages sent through acoustic signals. Outside the hull, pressure increased relentlessly. Inside, Cameron sat alone in a small bubble of air, listening to the quiet hum of systems and watching instruments track his progress. Along the way, flashes of bioluminescence appeared outside the viewports, brief sparks of living light in the surrounding black. Eventually, the sub passed onto the abyssal plain and continued downward. At last, the depth gauge settled near 10,900 meters. After more than 2.5 hours of descent, Cameron reached Challenger Deep. What greeted him was both stark and surreal. The sea floor stretched out as a flat expanse of fine, pale sediment, illuminated only by his lights, a silent desert at the bottom of the ocean. Within the beams, small amphipods drifted and crawled, evidence of life, persisting even here. Cameron maneuvered carefully, collecting samples and recording footage with high-resolution cameras. He remained on the bottom for nearly 3 hours longer than any human before him. Alone inside the submersible, he was for that moment the only person on Earth at the deepest point of the planet, suspended beneath billions of tons of water in complete darkness. Later, Cameron described the descent as deeply isolating, yet profoundly awe-inspiring. The silence, the stillness, and the awareness of his location combined into something almost unreal. He likened it to being on another planet, a frontier vast, ancient, and utterly indifferent to human presence. Unlike astronauts who can look out into star-filled skies, Cameron faced a different kind of infinity. Beyond his lights was nothing but darkness, complete and unbroken. And yet, within that narrow cone of light, there was life. Sediments, small moving creatures, and subtle geological textures quietly revealed stories shaped by pressure and time beyond human scale. The dive was more than a personal milestone, it was a scientific achievement. Samples collected from the trench later revealed microorganisms with remarkable adaptations, offering new insights into how life survives under extreme pressure and cold. The footage Cameron captured gave the world its clearest view yet of Challenger Deep, transforming it from an abstract depth measurement into a tangible place. His success demonstrated that modern technology could once again reach the deepest point on Earth, reopening the door for future exploration. For Cameron, the journey also represented a fusion of storytelling and discovery. He had spent his career creating imaginary worlds on screen, but this time he had entered one of Earth's true alien landscapes. What he brought back was not fiction, but evidence. Proof that this frontier still exists, still functions, and still holds unanswered questions. The symbolism of the solo descent resonated widely. 50 years after two men had made the journey together, one person went alone. It highlighted how exploration can be both technological and deeply personal. Seated inside a steel sphere, scarcely larger than a closet, Cameron carried with him the curiosity of countless people who had long wondered what lay at the bottom of the sea. When he resurfaced nearly 7 hours later, support ships and crews were waiting, tracking a mission that had captured global attention. The dive was celebrated not only by scientists, but by the public. It served as a reminder that exploration did not end with the space race. Even on our own planet, frontiers remain that are as demanding and mysterious as anything beyond Earth. And yet, despite the achievement, the trench itself remained largely unknown. Cameron explored only a tiny fraction of Challenger Deep. The flat plain he saw was just one small part of a vast and complex region. Even today, each expedition uncovers new details, new species, and new questions. Cameron's journey was not a conclusion, but a continuation, another step in humanity's slow unveiling of the abyss. The Deep Sea Challenger dive reminded the world that the Mariana Trench is not merely a line on a chart, it is a real place, a living environment, one that can be reached, studied, and experienced, and one that still waits quietly in the dark. For Cameron, the dive was the fulfillment of a lifelong dream. For science, it marked a turning point, and for the rest of us, it offered a rare glimpse into a world that feels impossibly alien, yet exists right here on our own planet. Still, despite the drama and courage required to place a human inside a submersible and lower them to the deepest point on Earth, most exploration of the Mariana Trench has not been carried out by people at all. It has been done by machines. Robotic explorers have become the true workhorses of deep sea science. They do not need oxygen. They are unaffected by darkness, isolation, or fear. They do not tire, and their metal bodies can be designed specifically to endure the crushing pressure of the abyss. While human descents remain powerful symbols, the steady accumulation of knowledge from the trench has largely come from robots built to go where humans rarely can. These machines take many forms. Some are free-falling landers, heavy frames equipped with cameras, sensors, and bait. Released from the surface, they sink slowly through the water column, drifting downward until they settle on the seafloor. There, they quietly record whatever passes through their lights, either transmitting data upward or storing it until recovery. Others are remotely operated vehicles tethered to ships by long cables and guided by pilots who sit far above the ocean, steering through screens and instruments. There are also autonomous vehicles programmed to navigate on their own, making decisions without direct human control as they explore the depths. The first robotic missions to Challenger Deep began decades after the Trieste dive. In the 1990s, Japan's remotely operated vehicle, Kaiko, made repeated descents to the trench, capturing video and collecting samples from the seafloor. For the first time, scientists could observe life at the deepest point on Earth for extended periods rather than fleeting moments. Amphipods and other organisms appeared regularly in its footage, confirming that the trench was not barren, but active and alive. Later, the United States developed advanced systems such as Nereus, a hybrid vehicle capable of operating both autonomously and under remote control. In 2009, Nereus reached Challenger Deep, adding new data to the growing picture of the abyss. Yet even these machines are not immune to the environment they explore. Pressure remains unforgiving. Electronics must be sealed inside protective housings designed to withstand more than 1,000 atmospheres. Cables must resist crushing and abrasion. And sometimes, despite careful engineering, failure occurs. In 2014, Nereus was lost in the Kermadec Trench, destroyed by the very forces it was built to survive. Still, robots hold clear advantages over human explorers. They can remain in the trench far longer. Where a crude submersible is limited by oxygen power and human endurance, robotic vehicles can operate for days. They can be deployed again and again, each mission adding another layer of data. And because no human life is at risk, they can be built smaller, more efficient, and sometimes more daring. Quietly, methodically, these machines continue to expand our understanding of the deepest place on Earth, one descent at a time. A robot does not hesitate as it sinks into the abyss. It feels no fear, no anticipation, only the steady execution of its instructions. Because of that, these machines have become our most consistent witnesses to the deepest parts of the ocean. The images they return are quietly astonishing. Cameras reveal wide plains of fine sediment stretching into darkness, sometimes smooth and undisturbed, sometimes etched with faint trails left by animals moving slowly across the seafloor. Amphipods often appear in sudden swarms around bait emerging from the shadows with surprising speed. On other dives, pale snailfish drift calmly through the frame, their soft bodies perfectly adapted to pressures that would destroy surface creatures. Occasionally, strange jelly like forms float past translucent and unfamiliar. Each frame confirms the same truth. Life persists where we once believed none could exist. Robots do more than observe, they collect. Mechanical arms open containers at depth, lifting samples of mud water and living organisms from the trench floor. When these samples return to the surface, they tell deeper stories. Scientists discover microbes that survive by metabolizing chemicals in ways unknown elsewhere, their cells stabilized against crushing pressure. These findings reach far beyond oceanography. They inform biotechnology, medicine, and the search for life beyond Earth, offering clues about how biological systems might function in environments once thought uninhabitable. The trench is also a geological laboratory, and robotic explorers have transformed our understanding here as well. Using sonar and sensors, they map the contours of the seafloor, trace fractures, and record subtle seismic signals. Through these measurements, scientists confirm the ongoing process of subduction where the Pacific Plate is forced beneath the Mariana Plate. The sediments and rocks gathered from the trench reveal the slow but powerful movements shaping Earth's crust. What was once invisible becomes data, and that data reshapes how we understand the planet itself. For the people guiding these machines, the experience is indirect, but no less intense. Instead of looking through a viewport, they sit in control rooms aboard ships watching glowing screens as their vehicle descends into darkness. Joysticks guide robotic arms. Numbers scroll across monitors. Cameras illuminate only a small cone of seafloor ahead surrounded by blackness. There is a strange tension in knowing the machine is kilometers below, connected by cables that feel fragile against the immensity of the ocean. And in any moment, a malfunction could mean permanent loss. Each mission carries both precision and risk. Even with their advantages, robots face a fundamental limitation scale. The trench stretches for hundreds of kilometers, and each dive explores only a tiny fragment. Vast slopes, hidden basins, and unexplored folds remain untouched. The picture we have is still incomplete, assembled piece by piece. Yet with every successful mission, the unknown retreats slightly. Amphipods at record depths. Snailfish surviving beyond expected limits. Microbes thriving under extreme pressure. Sediments recording tectonic history. Each discovery adds another tile to the mosaic. As technology advances, robotic explorers will go deeper, remain longer, and see more than ever before. For now, they are our most reliable eyes in the abyss. Human descents capture imagination, but robotic dives quietly carry the work forward, returning again and again, extending human knowledge into a world we cannot yet inhabit ourselves. When robotic explorers return from the trench, attention often lingers on the unfamiliar animals drifting through the darkness or moving slowly across the seafloor. Yet beneath those living forms lies something just as significant, though silent and immobile, the geology itself. The Mariana Trench is not merely a deep depression in the ocean floor. It is the visible expression of one of the most powerful and enduring processes in Earth's history, a process that has shaped continents, raised mountain ranges, triggered earthquakes, and fueled chains of volcanoes. To understand the trench is to glimpse the inner machinery of the planet. The trench exists because of subduction along the western Pacific. Here, the Pacific Plate, one of the largest slabs of Earth's outer shell, is slowly being forced beneath the smaller Mariana Plate. The motion is almost imperceptible, only a few centimeters each year, comparable to the growth of fingernails. But over millions of years, this steady movement accumulates, bending the seafloor downward and dragging entire sections of crust into the mantle below. One way to imagine this is to picture Earth's crust as a massive mosaic of plates, each thousands of kilometers across, floating atop a hotter, softer interior. These tectonic plates drift, collide, and separate, carrying oceans and continents with them. Where plates collide, different outcomes emerge. Some collisions push crust upward, forming mountain ranges like the Himalayas. Others slide sideways, creating long fault systems. But in places like the Mariana Trench, one plate sinks beneath another, recycling old crust deep into the planet. At Challenger Deep, this downward bending reaches its most extreme expression. The Pacific Plate curves sharply, pulled into a long arc as it descends into the mantle. The seafloor here is not simply low, it is flexed and warped by immense forces acting over geological time. Above this boundary, the Mariana Islands rise as a visible consequence of what happens below. As the sinking plate is carried, deeper heat and pressure cause it to release water and other trapped fluids. These fluids migrate upward into the overlying mantle, lowering the melting point of the surrounding rock. Magma forms, rises, and eventually erupts at the surface, building volcanoes and island chains. The islands stretching above the trench are therefore not separate from it. They are directly connected surface expressions of the same deep process. Without subduction, the Mariana Islands would not exist. The trench and the islands are two sides of the same geological system, one hidden in darkness, the other visible beneath the sky. For geologists, this makes the Mariana Trench an invaluable natural laboratory. Subduction has shaped Earth for billions of years, building continents, closing oceans, and recycling material between the surface and the interior. The trench is not the only place where this happens, but it is the deepest and therefore the most extreme. Its depth offers a rare opportunity to study how plates behave under maximum stress. Every sonar map, every sediment sample, and every seismic reading collected from the trench adds to our understanding of how the planet functions. Earthquakes are a natural part of this picture. As the plates grind and lock against each other, stress accumulates. When that stress is released, the result is seismic motion that can ripple through the crust and across the ocean. The trench is not a static feature. It is active, shaped continuously by forces still at work today. In this sense, the Mariana Trench is not just a destination for exploration. It is a living record of Earth's dynamics, a place where the slow movement of plates becomes visible in the most dramatic way possible. Beneath the silence and darkness lies the restless engine of the planet itself, quietly reshaping the world above. At times, the stress locked between tectonic plates is released suddenly, sending shock waves through Earth's crust. The Mariana region is highly active in this regard, producing earthquakes that range from subtle tremors detectable only by instruments to powerful events capable of shaking islands and generating tsunamis. For communities living around the Western Pacific, these quakes are reminders that the trench is not an abstract feature on a map, but a dynamic force that can directly affect human lives. The immense geological energy concentrated in the trench does not remain hidden in the deep. It reaches the surface through sudden, sometimes violent expressions. Volcanoes are another visible sign of this connection. Beneath the ocean, submarine volcanoes rise from the seafloor, some quietly dormant, others still active. Above the water, the Mariana Islands themselves are volcanic, built layer by layer by eruptions spanning millions of years. Subduction creates magma, and magma builds volcanoes. The trench and the volcanic arc are inseparable parts of the same system. To study one is inevitably to study the other. Yet the geology of the trench holds insights that go far beyond earthquakes and volcanoes. The sediments accumulating at the bottom act as a long-term record of Earth's history. Year after year, tiny particles settle through the water column, carrying chemical signatures of the ocean and atmosphere above. By extracting sediment cores and analyzing their layers, scientists can reconstruct past climates, shifts in ocean circulation, and even the rhythms of ice ages. In this way, the trench functions as a natural archive, a library where Earth's environmental history is written and preserved under immense pressure. The rocks themselves tell another story. Under the extreme pressures found in trenches, minerals transform into structures rarely seen at the surface. These high-pressure minerals offer clues about what happens as crust is dragged deep into the mantle. Some forms of matter, created naturally in trenches, are so rare that they are difficult to reproduce, even in advanced laboratories. Studying them helps scientists understand how heat and material flow inside the planet, driving the slow but relentless motion of tectonic plates. Robotic explorers have been crucial in uncovering these hidden details. Cameras have recorded underwater landslides cascading down trench walls after earthquakes. Sensors have detected chemical plumes rising from the seafloor, evidence of fluids escaping from the sinking plate. Seismic instruments trace vibrations moving through rock kilometers below the surface. Each observation adds another piece to a complex puzzle linking biology, geology, and chemistry into a single interconnected system. For many people, the Mariana Trench ultimately represents scale, not only in depth, but in time. The forces that shaped it began millions of years ago and will continue millions of years into the future. The Pacific Plate will keep sliding. The trench will continue to evolve. Volcanoes will erupt, and earthquakes will rumble on long after individual human lives have passed. We cannot perceive these changes directly, but the geology speaks of deep time, of a planet that moves according to rhythms far slower than our own. And just as life has adapted to darkness and crushing pressure, it has also adapted to this restless geology, finding ways to persist in a world shaped by constant motion beneath the seafloor. Near subduction zones, hydrothermal vents release fluids rich in dissolved chemicals, creating pockets of life in places where sunlight never reaches. Around these vents, microbes and larger organisms gather, forming ecosystems powered not by the sun, but by Earth's internal heat and chemistry. In environments like the Mariana Trench, the boundary between geology and biology begins to dissolve. Rock water pressure, heat, and life are no longer separate forces. They shape one another continuously. The trench's hidden geology expresses itself everywhere: in the volcanic island arcs above, in earthquakes that ripple through the crust, in sediments that quietly record deep time, and in living systems that exist only because the chemistry of the earth makes them possible. To explore the trench is, in a very real sense, to explore the planet itself, its restless crust, its deep interior, and its endless cycle of destruction and renewal. When scientists talk about life at the bottom of the Mariana Trench, they often pause not for drama, but for disbelief. The conditions combine every extreme imaginable. Pressure exceeds 1,000 times that at the surface. Temperatures hover just above freezing. Sunlight never arrives. Food is scarce and unpredictable, and yet life persists not barely, but effectively. Studying these organisms pushes biology to its limits, revealing just how flexible the rules of life can be. The foundation of trench ecosystems is microscopic. Beneath the mud that looks lifeless to the naked eye, sediments are packed with microbes. These organisms do not rely on photosynthesis. Instead, they harvest energy from chemistry itself using compounds such as hydrogen, methane, and sulfur that seep from rocks or arrive dissolved in the water. This process, known as chemosynthesis, replaces light as the engine of life. For these microbes, chemistry is enough. Many are extremophiles organisms whose proteins, membranes, and enzymes are structured to remain stable under crushing pressure. Some of their enzymes only function at depth and fall apart when brought to the surface. These adaptations are so specialized that scientists study them not only to understand Earth's deep biosphere, but to imagine how life might survive beneath the ice of Europa or Enceladus, or in subsurface oceans on distant worlds. Larger creatures build their lives on this microbial foundation. Amphipods, shrimp-like crustaceans, are among the most abundant animals in the trench. At depths beyond 10,000 meters, they arrive quickly at baited traps, their translucent bodies catching the glow of submersible lights. They are opportunistic feeders, consuming marine snow drifting from above, or scavenging the remains of larger animals that sink into the abyss. Remarkably, some amphipods from Challenger Deep have been found carrying traces of industrial pollutants, a sign that even the deepest ecosystems are connected, however faintly, to human activity at the surface. Despite this, they flourish in conditions that appear overwhelmingly hostile. Among the most surprising residents of the trench are snailfish, the deepest living vertebrates ever observed. Pale, soft bodied, and almost gelatinous, they appear fragile by surface standards. Yet at depth, they are perfectly adapted. Their skeletons are reduced, their muscles modified, and their cells stabilized by chemical compounds that protect them from pressure. They move slowly across the seafloor, feeding on amphipods and other small prey. Their discovery at depths beyond 8,000 meters challenged long held assumptions about how deep vertebrate life could exist. Seeing a fish thrive under such conditions forces a reconsideration of where biological limits truly lie. Scarcity defines life in the trench. Unlike surface ecosystems powered by sunlight, the deep ocean depends on a slow, constant drizzle of organic material known as marine snow. Tiny particles of dead plankton, waste, and fragments of larger organisms fall through the water column over weeks or even months. For trench life, this faint rain of nutrients is precious. Nothing is wasted. Every fragment is recycled, every molecule reused. From microbes to crustaceans to fish, the ecosystem is built on efficiency, patience, and adaptation. Most of that drifting organic material is intercepted long before it ever reaches the abyss. It is consumed in the upper and middle layers of the ocean, recycled again and again as it moves downward through the water column. By the time it nears the bottom of the Mariana Trench, only a thin remnant remains. And yet that faint remainder is enough. It sustains entire communities living under pressures that would crush nearly all other forms of life. In the trench, scarcity is normal. Every organism is shaped by it. Feeding is slow, deliberate, and efficient. Nothing is wasted because nothing can be replaced easily. Occasionally, however, the quiet economy of the deep is interrupted when the body of a whale or large fish sinks into the trench. It becomes an event of enormous significance. These rare falls act like sudden oases, drawing scavengers from far away. Amphipods arrive first, swarming in great numbers, stripping flesh with remarkable speed. Microbes follow, breaking down what remains. For months or even years, a single carcass can support life, injecting a burst of energy into an otherwise sparse system. These moments reveal how closely trench ecosystems are tied to the surface world, dependent on what slowly rains down from above. What allows trench animals to survive such extremes is not strength, but chemistry. Many species contain unusually high concentrations of a molecule called trimethylamine N-oxide, or TMAO. This compound stabilizes proteins under immense pressure, preventing them from deforming or collapsing. The deeper a species lives, the more TMAO it tends to have. It functions like an invisible scaffold, holding cellular machinery in place while the weight of the ocean presses in from all sides. Without it, life at these depths would be impossible. This chemistry reshapes our understanding of biology. On the surface, life is powered almost entirely by sunlight. Plants and algae convert light into energy, forming the base of food chains. In the trench, sunlight plays no role at all. Instead, life relies on chemical energy. Microbes feed on methane, hydrogen, sulfur, and other compounds released from rocks and sediments. From them, energy flows upward through the ecosystem. It is a complete biological system operating without the sun, a reminder that light is not a requirement for life, only one of many possible pathways. For scientists, this realization has far reaching implications. If life can thrive in the crushing cold darkness of the Mariana Trench, then similar environments elsewhere may also be habitable. Subsurface oceans beneath icy moons like Europa or Enceladus suddenly seem less implausible. The trench becomes more than an earthly curiosity. It becomes a model, a proof of concept for life beyond familiar boundaries. There is also something quietly humbling about trench life. Humans often think of themselves as adaptable, but our survival depends on a narrow band of conditions. Air warmth, light, and pressure all must fall within specific limits. Trench organisms require none of these comforts. They are not visitors in their world. They belong to it completely. What seems hostile to us is ordinary to them. Yet even this remote world is no longer isolated. Studies have found traces of plastics, industrial chemicals, and persistent pollutants in trench organisms. These substances travel slowly, sinking particle by particle, eventually reaching even the deepest points on Earth. Their presence is a reminder that no place is entirely beyond human influence. Life in the trench has adapted to darkness and pressure over millions of years. Now it must also contend with the byproducts of a surface civilization it will never see. Still, resilience defines the abyss. Life continues adjusting again, finding new balances. The trench teaches us that limits are rarely absolute. They are thresholds, places where familiar rules give way to new solutions. And as we learn more about this hidden world, it becomes clear that the Mariana Trench is not the end of life, but one of its most extraordinary expressions. When scientists first lowered cameras and sampling equipment into the Mariana Trench, many believed they were entering a world beyond human reach, a place so deep, so dark, and so hostile that it would remain untouched by our influence. Nearly 11 kilometers of water lay above it, sealing the trench beneath crushing pressure and permanent night. It seemed impossible that anything from the surface could ever arrive there, but when the instruments returned, that assumption quietly collapsed. Even at the deepest point on Earth, signs of human activity were present. The trench, once imagined as pristine, had become a silent archive of our civilization's most persistent waste. In 2017, remotely operated vehicles recorded something deeply unsettling: a plastic bag resting on the seafloor of Challenger Deep. It lay motionless on the mud, intact, as if time itself had slowed around it. Since then, more debris has been documented: food wrappers, plastic fragments, pieces of packaging objects designed for convenience now preserved in the abyss. This is not accidental. Each year, millions of tons of plastic enter the ocean. Sunlight and waves break larger items into smaller pieces, but they do not destroy them. Over time, Gravity pulls this material downward. Slowly, inevitably, it sinks. Given enough time, much of it reaches the deepest places on the planet. The trench is not protected by its depth. It is simply the final destination. More disturbing still are the things we cannot easily see. Microplastics fragments smaller than grains of sand have been found embedded in sediment from Challenger Deep. These particles are now part of the mud itself, mixed into the environment where extreme life survives. They have also been detected inside amphipods collected from the trench, proving that plastic has entered the deepest food chains on Earth. Synthetic material created at the surface now circulates inside organisms living under more than 1,000 atmospheres of pressure. Chemical pollution has followed the same path. Studies of trench amphipods have revealed high concentrations of PCBs, toxic industrial compounds, once widely used in electrical equipment, and plastics. Although banned decades ago, these chemicals resist breakdown. They drift through air and water, attach to particles, and sink slowly through the ocean until they reach its lowest point. There, they accumulate not diluted, but concentrated cycling through organisms that evolved long before such substances existed. The implication is difficult to ignore. The Mariana Trench was once imagined as untouched a final frontier beyond human influence. Instead, it has become proof of how completely our actions permeate the planet. Plastics and pollutants, born in cities and factories, now rest beside life forms adapted to eternal darkness. Creatures that evolved to survive pressure and scarcity now ingest materials their biology never anticipated. The trench does not reject our waste, it absorbs it. What was once thought to be pure is now marked by us. The deepest place on Earth, hidden beneath miles of water, has become a mirror reflecting not our technological achievement, but our reach, our persistence, and the unintended consequences of our presence. And yet, even within this altered environment, life continues. Amphipods still gather in great numbers, feeding and reproducing, despite carrying traces of pollutants in their bodies. Microbial communities remain active in sediments, threaded with microplastics, breaking down chemicals and sustaining the base of the food web. This resilience is extraordinary, but it does not cancel out the concern beneath it. Adaptation does not mean immunity. The changes that allow survival under contaminated conditions may come with hidden costs. Slower growth, altered reproduction, subtle shifts in metabolism that ripple outward through an already fragile ecosystem. The trench is not like a forest or a coral reef where impacts can be observed year after year. Its remoteness and depth conceal consequences, making them difficult to measure and even harder to predict. What happens down there unfolds slowly, silently, beyond regular human observation. For explorers, encountering human waste at the bottom of the world is profoundly unsettling. To descend into a place so extreme, so alien to surface life, and to find a plastic bag resting on the mud is to confront an uncomfortable truth. There is no true separation between the surface and the abyss. The ocean is a single connected system. What we release near shorelines does not disappear. It travels fragments, sinks, and eventually settles in the deepest places we know. There is a quiet irony in this. Many of the materials we discard will outlast us. Plastics persist for centuries. Certain industrial chemicals endure even longer, while after cities are rebuilt and technologies replaced, fragments of today's packaging may still lie embedded in trench sediments. In this way, the Mariana Trench has become more than a record of Earth's natural history. It has become an unintended archive of human activity, a layer of civilization preserved alongside layers of geology and climate. And still life endures. Amphipods filled with synthetic compounds continue to swarm baited traps. Microbes in polluted mud continue their chemical work. The ecosystem functions even with our waste woven into its foundation. This persistence is not a justification. It is a warning. Survival does not mean absence of harm. It means that life is being pushed to adapt yet again, this time to conditions we have imposed. For scientists, the trench now serves two roles at once. It remains a natural laboratory, revealing how pollutants move through the ocean, how they concentrate, and how they enter food webs. But it is also a cautionary tale, a demonstration that no environment is truly isolated and that the consequences of surface activity eventually reach even the most remote extremes. In the stillness of Challenger Deep, amid amphipods and snailfish, amid sediments shaped by pressure and time, fragments of plastic drift quietly. They do not dissolve. They do not announce themselves. They simply remain silent markers of our presence in a place we rarely see. And this realization leads to another line of thought. If pollution can reach the deepest ocean, then the trench is not only connected to human activity, but also to broader questions about life beyond Earth. The same adaptations that allow organisms to survive in mud laced with plastics and chemicals offer clues about how life might persist in other extreme environments. When researchers first discovered thriving microbial communities in the sediments of Challenger Deep, they began to view the trench not just as a remote part of our planet, but as an analog for other worlds. The conditions there are severe. By any standard, immense pressure near freezing temperatures, perpetual darkness, and limited energy. And yet life has not only survived, it has organized itself into functioning ecosystems. In that sense, the trench stands at an intersection. It reflects both the resilience of life and the reach of human influence. It reminds us that life can persist under extraordinary stress, but also that no corner of Earth is untouched by what we do above. In both cases, exploration demands humility. Whether descending into the ocean or launching into space, humans must acknowledge environments that are fundamentally hostile to our bodies. In the trench, pressure threatens to crush every structure. In space, the lack of pressure threatens to tear life apart. One environment presses inward, the other pulls outward. Yet the engineering challenge is similar. How do you create a fragile pocket of safety in a place that does not care whether you survive? This parallel is why astrobiologists pay such close attention to the deep ocean. The Mariana Trench is not just a geological feature or a biological curiosity. It is a proving ground, a place where hypotheses about life adaptation and survival can be tested without leaving Earth. Every successful descent, every functioning instrument, every organism discovered under extreme pressure, adds confidence to the idea that life elsewhere is possible. The trench also reshapes how scientists think about habitability. For a long time, the search for life focused on what is called the habitable zone, the region around a star where liquid water can exist on a planet's surface. But worlds like Europa and Enceladus challenge that idea. Their surfaces are frozen and hostile, yet beneath them may lie vast oceans warmed by tidal forces and internal heat. The Mariana Trench shows that surface conditions can be misleading. What matters is not sunlight alone, but energy chemistry and time. Life in the trench operates slowly. Metabolisms are reduced. Growth takes longer. Reproduction is measured and sparse. Energy is conserved with extraordinary efficiency. This slowness may be a common trait of life in extreme environments. On distant moons, life, if it exists, may not flourish in abundance or speed, but in patience. Quiet ecosystems cycling chemicals over millennia, unseen and unnoticed. There is something deeply grounding about this idea. We often imagine extraterrestrial life as dramatic or threatening, but the trench suggests something far more subtle: life that persists rather than dominates, life that adapts rather than conquers, one that exists not in spectacle but in balance with harsh surroundings. In this way, the deepest ocean teaches restraint. It reminds us that intelligence and complexity do not always come with size, speed, or visibility. Some of the most successful organisms on Earth are invisible to the naked eye, living quietly in mud under crushing pressure, shaping chemical cycles that sustain entire ecosystems. As scientists lower probes into Challenger Deep, they are not only collecting data, they are rehearsing for the future. Learning how to operate instruments where repair is impossible, learning how to communicate through hostile media, learning how to trust machines operating far beyond direct human reach. These lessons translate directly to space exploration, where probes must function autonomously millions of kilometers from Earth. The trench then becomes a bridge, a place where oceanography, geology, biology, engineering, and astronomy meet. A reminder that exploration is not divided into Earth science and space science, but united by a single question: how does matter organize itself into life under extreme conditions? And perhaps most importantly, the trench reframes our sense of rarity. If life can thrive beneath 11 kilometers of water in darkness, cold pressure, and scarcity, then the universe may be more alive than we once imagined. Not necessarily crowded with civilizations, but seeded with quiet, persistent forms of biology wherever energy and chemistry allow. The Mariana Trench does not promise an answers about aliens or distant worlds, but it offers something just as valuable: perspective. It tells us that life is not fragile in the way we once thought. It bends, it adapts, it waits, and it finds a way to persist in places we are only beginning to understand. From that understanding, the abyss is no longer just the bottom of the earth. It becomes a window outward, a reminder that the most alien environments may not be light years away, but already beneath our feet, hidden in darkness, patiently reshaping what we believe life can be. And so the exploration of the deep ocean and the exploration of space continue to inform and mirror one another. Each new descent into the abyss refines the technology's methods and mindset that may one day carry us to distant worlds. Every pressure resistant hull, every sensor that survives crushing depths becomes a lesson in how to endure hostile environments beyond Earth. In this way, the trench is not just a destination of study, but a training ground for interplanetary discovery. At the same time, the questions we bring with us shape what we find. When scientists search the deep sea for life without sunlight, they are also rehearsing how to search for life on icy moons beneath frozen crusts or in atmospheres unlike our own. The strange organisms of the abyss remind us that life does not follow a single blueprint. It adapts, persists, and evolves in ways that stretch our imagination. This understanding expands the boundaries of what we consider habitable, both on Earth and beyond it. There is also a quieter lesson in these explorations. They teach patience. Progress in both realms is slow, deliberate, and often invisible to the outside world. Years of preparation may lead to only a few hours of observation, yet those moments can reshape our understanding of reality. In the darkness of the trench and the silence of space, discovery rarely arrives with spectacle. It emerges in subtle signals, faint patterns, and careful interpretation. Ultimately, the abyss and the cosmos confront us with the same truth. Exploration is as much an inward journey as an outward one. By pushing into environments that dwarf us in scale and power, we are forced to confront our limits, our fears, and our assumptions. What we gain in return is not dominance over these realms, but perspective, a deeper awareness of our place in a vast and interconnected universe. Perhaps that is why we keep listening, keep descending, keep looking up. Whether through a porthole at the bottom of the sea or a window aboard a spacecraft, we are drawn by the same impulse to understand what lies beyond the edge of the known. And in doing so, we discover that the greatest unknown is not the darkness around us, but what we may yet learn about life, resilience, and ourselves. In both situations, our minds drift toward what might be hidden just beyond human reach. Yet we do not actually need to invent these possibilities. The truly alien already exists here on Earth in the depths of the trench. These organisms are tiny, enduring, often glowing, and profoundly unfamiliar. They survive in conditions as extreme as anything we might expect on distant planets. Their existence suggests that the universe may not be filled with life that resembles us, but with life shaped to thrive in environments we once believed could never support it. To recognize life elsewhere, we may need to think less like gardeners, nurturing familiar plants, and more like biologists, carefully observing amphipods in the dark. The abyss and the stars are linked not because they are identical realms, but because together they expand our understanding of what life can be and where it can persist. The trench proves that life can flourish in perpetual darkness under crushing pressure without sunlight. The stars remind us that countless worlds may exist under similar conditions. One realm lies beneath our feet, the other far above our heads, and together they frame the enduring question of whether life in the universe is rare or widespread, fragile, or inevitable. Long before sonar traced the ocean floor or submersibles carried humans into the depths, people gazed at the sea and wondered what lay below. Even the surface alone was enough to inspire awe and dread, vast and restless, stretching beyond the horizon. For sailors who ventured out of sight of land, the ocean was both a lifeline and a threat, a source of sustenance and a constant reminder of danger. When imagination met ignorance, the unseen depths became fertile ground for myth. The abyss hidden from view turned into a stage for stories that explained fear and uncertainty. Across many ancient cultures, the sea was seen as a domain of chaos, a force beyond human control, inhabited by beings of immense power and unpredictability. Greek legends spoke of Poseidon wielding his trident to summon storms and earthquakes. In Mesopotamian belief, the primordial sea took form as Tiamat, a dragon embodying disorder and creation alike. Norse mythology imagined the Midgard serpent so enormous it encircled the world beneath the waves. These stories reveal how people understood the deep not as empty space, but as a living realm filled with forces beyond comprehension. Even as seafaring knowledge advanced and coastlines were mapped, the unknown parts of the ocean remained marked by caution and fear. Medieval maps often placed warnings at the edges of the known world. Illustrations of dragons, krakens, and colossal sea serpents filled the margins, their bodies exaggerated their scale, terrifying. To those who sailed wooden ships across unpredictable waters, the depths were believed to conceal creatures capable of capsizing vessels, pulling sailors into darkness, and consuming entire fleets without a trace. Some of these legends likely began with real encounters. A giant squid briefly breaking the surface, a whale rising suddenly from below, or a vast school of fish moving like a living shadow could easily become something far more terrifying in memory. Over time, these moments were magnified and reshaped, turning into enduring symbols of the deep. The farther down people imagined the ocean extended, the more unfamiliar and fantastic its inhabitants became. Among the most persistent figures were mermaids appearing across cultures in many forms. Sometimes they were kind and enchanting, other times deceptive or deadly. Half human and half fish, they embodied the fragile boundary between land and sea. Sailors swore they had seen them, and illustrations found their way into maps and manuscripts. Whether inspired by distant sightings of manatees and dugongs or born entirely from imagination, mermaids became a powerful part of ocean mythology. They represented temptation, danger, and mystery woven into a single image. As literature evolved, so did humanity's fascination with the deep. The 19th century, marked by scientific progress and global exploration, produced some of the most influential stories about the ocean's hidden world. Jules Verne's 20,000 Leagues Under the Sea introduced readers to Captain Nemo and the submarine Nautilus, guiding them through a richly imagined realm beneath the waves. Verne described enormous squids, sprawling coral landscapes, and silent shipwrecks resting on the sea floor. Though fictional, his work echoed the scientific spirit of the era, blending known facts with bold speculation. For many readers, it was the first time the ocean was imagined as a place that could be explored in detail, not merely crossed. Later, writers took the symbolism of the deep in darker directions. H.P. Lovecraft and other authors of cosmic horror transformed the ocean into a metaphor for the unknowable. In Lovecraft's stories, ancient beings slept beneath the waves, hidden in trenches, and waiting beyond human awareness. Here, the abyss was not only physically deep, but psychologically unsettling, suggesting that humanity might be insignificant within a far larger and more indifferent reality. These ideas have never fully faded. Even today, films, novels, and games return to the ocean as a setting for suspense and unease, drawing on the same mixture of curiosity and fear. Yet this cultural legacy is not purely dark. For many traditions, the sea has also been a source of beauty, meaning, and connection. Myths speak of underwater palaces and divine kingdoms, places of elegance and wonder hidden beneath the surface. In Japanese folklore, the Dragon King's palace, Ryugujo, lies beneath the sea, filled with splendor and magical treasures. In Polynesian cultures, the ocean is not a barrier, but a bridge linking islands' ancestors and spirits across vast distances. Modern storytelling continues to reflect this dual nature. Films like The Abyss imagine first contact with an alien intelligence, not among the stars, but beneath the ocean floor. Nature documentaries portray bioluminescent creatures drifting through darkness like constellations in motion. Even children's stories often place secrets, magic, and discovery beneath the waves. The trench itself, though rarely named outright, becomes the ultimate symbol of depth, the place where all mysteries seem to gather. What ties together these myths, stories, and artistic visions is the idea of the deep ocean as a threshold. It exists just beyond easy reach, accessible only with risk and effort. It marks the point where the familiar world ends and something unknown begins. For ancient sailors, this boundary signified danger and loss. For modern scientists, it represents opportunity and knowledge. For writers and artists, it is an endless source of inspiration, a space onto which fear, wonder, and possibility can be projected. As the deepest region of that ocean, the trench embodies the final boundary. It is the edge of the charted world, the bottom of the map, the place where human technology strains and imagination continues to descend. And even now, as we learn more about it, the trench remains a reminder that there are still depths, both physical and conceptual, where our understanding has yet to reach. Many of the oldest sea legends probably trace back to genuine moments at sea. A colossal squid surfacing for seconds, a whale erupting from the depths without warning, or an immense shoal of fish flowing like a single moving shadow could easily transform into something far more ominous in the human mind. With time, these fleeting encounters grew larger than life, evolving into lasting symbols of the unknown below. The deeper people imagined the ocean to be the stranger and more unreal its creatures became. Mermaids stand out as some of the most enduring figures in these stories, appearing in countless cultures with striking similarities. At times, they were portrayed as gentle and mesmerizing, at other times, as treacherous or lethal. Neither fully human nor fully animal, they symbolized the fragile divide between land and sea. Sailors insisted they had seen them, and artists etched their forms into maps and old manuscripts. Whether inspired by brief sightings of manatees and dugongs, or shaped entirely by imagination, Mermaids took on a powerful mythic role, combining attraction, peril, and mystery into a single being. As storytelling matured, fascination with the ocean depths only intensified. The 19th century, driven by scientific curiosity and global exploration, gave rise to some of the most influential visions of the undersea world. Jules Verne's 20,000 Leagues Under the Sea invited readers aboard the submarine Nautilus, led by the enigmatic Captain Nemo, into a richly detailed realm beneath the waves. His descriptions of massive squids, vast coral formations, and forgotten shipwrecks resting in silence blurred the line between science and fantasy. Although fictional, Verne's work reflected the spirit of discovery of his time and helped many imagine the ocean as a place that could be explored and understood, not just crossed. Later authors pushed the symbolism of the deep into darker territory. H.P. Lovecraft and other writers of cosmic horror recast the ocean as a symbol of forces beyond human comprehension. In Lovecraft's universe, ancient entities slept beneath the sea, hidden in trenches far below awareness, waiting beyond the reach of reason. The abyss became more than a physical depth. It became a psychological one, suggesting that humanity might be insignificant when confronted with vast, indifferent powers. These themes still echo through modern culture. Contemporary films, novels, and games frequently return to the ocean as a backdrop for mystery and dread, drawing on the same tension between fascination and fear. Yet this legacy is not solely ominous. Across many cultures, the sea has also represented beauty, continuity, and meaning. Legends describe magnificent underwater realms and divine domains concealed beneath the waves. In Japanese folklore, the Dragon King's palace, Ryugujo, rests deep below the sea, filled with wonder and treasure. In Polynesian traditions, the ocean is not a dividing line, but a living pathway connecting islands, ancestors, and spirits across immense distances. Modern storytelling preserves this dual image. Films such as The Abyss imagine first contact with non-human intelligence, not in outer space, but beneath the seafloor. Documentaries reveal bioluminescent creatures drifting through darkness like living stars. Even children's tales often place magic secrets and discovery under the waves. The trench itself, though seldom named, directly becomes the ultimate metaphor for depth, the point where mystery feels most concentrated. What links these myths, stories, and artistic expressions is the idea of the deep ocean as a boundary. It lies just beyond ordinary reach, accessible only through danger, effort, and innovation. It marks where the familiar world ends and the unknown begins. To ancient sailors, this boundary meant risk and loss. To modern scientists, it signals knowledge waiting to be uncovered. To writers and artists, it offers an endless canvas for fear, wonder, and imagination. As the deepest part of the ocean, the trench represents that boundary in its purest form. It is the limit of the map, the lowest edge of the world we can touch, where technology is tested and imagination continues to descend. And even as exploration advances, the trench reminds us that there are still depths in the ocean and in our understanding that remain far from fully known. A new generation of deep diving submersibles is now taking shape, designed with far greater attention to safety, endurance, and human experience. Some concepts replace narrow viewing ports with transparent pressure spheres, allowing passengers to gaze directly into the abyss in every direction. Others imagine larger vehicles capable of carrying several people at once, transforming a descent that was once solitary into a shared journey. For the rare individuals who will one day reach the trench, the future may offer clearer views and longer stays, making it possible to feel the silence and crushing pressure in ways early pioneers like Picard Walsh or Cameron could scarcely have imagined. Beyond technology itself, another frontier is emerging cooperation across borders. Much like space exploration, deep ocean research is increasingly becoming a collective global effort. Countries with advanced capabilities, such as Japan, the United States, China, and others, are already investing heavily in next generation submersibles. In time, these parallel efforts may converge into shared systems networks of instruments anchored to the seafloor permanent observatories, quietly gathering data year after year. Such stations could monitor earthquakes, chemical shifts, and biological communities, continuously creating a long-term record of how trench environments change. Instead of isolated expeditions offering brief glimpses, humanity would gain an ongoing narrative of life and motion in the deepest parts of the ocean. At the same time, breakthroughs in materials science are reshaping what is possible. Engineers are developing alloys stronger and lighter than traditional steel ultra-resilient ceramics and composites engineered at the molecular scale. Together, these advances could produce submersibles that are faster, more efficient, and more reliable under extreme pressure. Improvements in battery systems promise longer missions, while advances in communication technology raise the possibility of real-time interaction with vehicles operating at full ocean depth. Step by step, these changes suggest a future in which the trench may become nearly as accessible to scientists as low Earth orbit is today. Yet with access comes difficult questions. Some see the deep ocean, including trench regions, as a potential source of valuable resources. Vast areas of the seafloor contain mineral-rich nodules formed over millions of years, holding manganese, cobalt, nickel, and other elements critical to modern technology. Extracting these materials could support industries on land, but the ecological consequences remain largely unknown. Deep sea ecosystems are delicate, slow to regenerate, and still poorly understood. As interest grows, the tension between economic opportunity and environmental responsibility is likely to sharpen. The future of deep ocean exploration, then, is not only about reaching new depths, but about the choices humanity makes along the way. It will involve balancing curiosity with restraint, knowledge with exploitation. Education and culture will play an important role as well. As more images, data, and stories from the trench reach the public, fascination with the abyss will continue to grow. Virtual reality experiences may one day allow anyone to simulate a descent, to look out over dark plains and glowing organisms without leaving home. Through documentaries, films, and interactive exhibits, the deep ocean will move from a distant, hidden frontier into a shared human experience, one that challenges us not only to explore, but to decide how we will care for what we discover. The trench, once confined to legend and imagination, may one day become part of common understanding. Yet, even with all these advances, it will never be fully revealed, no matter how many autonomous vehicles descend or how precise our maps become. The trench is simply too immense and too alive to be completely known. New species will continue to appear unfamiliar. Geological formations will be uncovered, and chemical processes we do not yet understand will persist in its depths. Exploration, then, is not a journey toward a final answer, but an ongoing acceptance that there is no true endpoint. The trench will always contain more than we can grasp. In studying it, we may discover as much about ourselves as we do about the ocean. Just as voyages into space have reshaped how we think about humanity's place in the universe, journeys into the deep may redefine our relationship with Earth. The trench presents resilience and vulnerability, side by side ecosystems thriving under crushing pressure, yet bearing unmistakable signs of human impact. To descend into this realm is to witness both the endurance of nature and the far reach of human influence. The future of exploration will therefore not be measured only in data collected, but in meaning understood. When we consider everything concealed within the Mariana Trench, it becomes clear that this vast scar on the seafloor represents more than extreme depth. It is an environment where pressure, darkness, and silence merge to reshape life itself. It stands as a reminder that our planet remains profoundly mysterious, and that even in an era of satellites and interplanetary probes, most of Earth is still unexplored. The trench is a frontier, but not one defined by borders or claims. It is a frontier of knowledge, imagination, and humility. Early explorers lowered ropes and weights into the ocean, stunned by the depths they measured. When Picard and Walsh descended in the Trieste, they carried with them humanity's enduring curiosity, proving that even the deepest abyss was not beyond reach. Decades later, James Cameron's solo descent in Deep Sea Challenger reframed the trench not merely as a barrier, but as an open invitation. Today, fleets of robots and sensors continue that journey, slowly revealing its secrets, layer by layer, grain by grain, life form by life form. And still, no matter how much is learned, the trench remains a realm beyond ordinary experience. To imagine standing at its bottom is to picture a silence so complete that only distant tremors disturb it. It is to envision a darkness so total that even powerful lights reveal only a small halo of sediment and drifting life before dissolving into blackness. It is to sense the immense weight of the ocean pressing in from all sides, a quiet reminder of forces far greater than ourselves. Yet, within that pressure and silence, life persists with remarkable ingenuity. Microbes convert chemistry into survival. Amphipods gather around rare scraps of nourishment. Snailfish move delicately through conditions that would crush almost anything else. Each adaptation is a quiet victory, evidence that life is not weak but endlessly creative, not confined but capable of expanding into even the most extreme niches. The trench does not show us where life ends, but how it transforms bending biology into forms that feel alien, yet belong fully to our world. At the same time, it reflects us back to ourselves. In plastic fragments, embedded in sediments, in pollutants, detected within deep sea creatures, we see unmistakable traces of human presence. The trench is not only a place of discovery, but a mirror revealing both the vast potential of life and the responsibility that comes with reaching into the deepest parts of our planet. Even the most remote depths bear the imprint of humanity, though no human hand ever touches them directly. The trench reflects our reach back to us, and with it, our responsibility. It reminds us that what we do on the surface travels farther than we imagine, settling quietly into places we will never see with our own eyes. At the same time, the trench serves as a bridge. It connects Earth to the wider universe, showing us that life does not require sunlight, that it can endure extremes, and that it can adapt to pressures and chemistries once thought unlivable. In the darkness of Challenger Deep, we catch a glimpse of what life might look like on Europa Enceladus, or distant worlds yet unknown. The abyss below our oceans and the abyss above our skies are bound by the same enduring question: where else can life exist? For centuries, the deep was filled with gods, serpents, monsters, and hidden kingdoms. Today, science has replaced myth with measurements, images, and discoveries. Yet the emotional response remains unchanged. Whether imagined as a realm of spirits or understood as an ecosystem of amphipods and snailfish, the trench continues to humble us, stretch our imagination, and remind us of how much lies beyond our understanding. Now linger with that thought. Imagine yourself descending slowly through the water, slipping past the final traces of sunlight through the dim twilight where blue fades into black, beyond the depths where whales dive and squid drift into endless night. Picture yourself sinking through kilometers of silence until you reach a wide, quiet plain of mud, extending into darkness in every direction. Around you, tiny organisms move softly, some glowing faintly, feeding without sound. Above you, 11 kilometers of ocean rise, like a vast invisible pillar, pressing down with immense weight. And yet life continues here, unaffected by whether it is observed or ignored. There is something deeply calming in this realization. The trench is not a story of domination or conquest. It is a story of existence. It has endured for millions of years and will remain long after we are gone. Our expeditions are brief interruptions, our instruments fleeting glances. The trench does not rely on us. It simply persists quietly, shaping its creatures, layering its sediments, absorbing the distant murmurs of earthquakes and storms. In that stillness, it offers perspective. It reminds us that Earth is older and larger than our ideas about it, that life is tougher and stranger than we expect, and that exploration is not about reaching a final answer, but about recognizing continuity. The trench is not the end of knowledge, it is the beginning of awe. So allow yourself to drift into that feeling. Imagine a place so deep that light has never reached it, so pressurized that even steel must yield, so silent that only distant echoes pass through. Picture amphipods moving slowly, snailfish gliding delicately, microbes laboring unseen. See the endless mud plains resting in complete darkness, held in perfect calm. Let that image settle within you like sediment sinking layer by layer, gently and without effort, until it feels like part of your own breathing. You are no longer at the surface. You are no longer bound by noise or brightness. You are drifting peacefully into the deep. Thank you for sharing this quiet journey with me. If it brought you comfort, kept you company, or helped you move closer to rest, you are always welcome to return. And if you wish to explore more calm reflections like this, you can choose to follow along or leave a small sign of support. It helps keep these gentle voyages alive, so we can continue wandering through the mysteries of science and the calm they offer. For now, let your thoughts settle like the sediments of the ocean floor. There is nothing else you need to do. Let your breath slow. Let the weight of the day sink away. And if sleep arrives, allow it to carry you softly as if you were drifting deeper into the quiet heart of the trench itself. Good night. Until next time, may your rest be as still and peaceful as the deepest waters.